Well, let me keep going. So our research laboratory is in biomedical Izmir Biomedicine and Genome Center, which is founded on 6550 under that law, and this is a very kind. It's on its kind of doing research plus it's not just the educational training researchers, but also try to find ways to startups your ideas of your research. All right, hopefully it will go, but I don't know why it's not going. All right, I think it did. All right. Okay, so if I step back and try to understand what we are doing basically, and what's the main field that we are working on is the laser tissue interaction, and there are different modes, several modes of laser tissue interaction, and we are focusing on it as a laboratory on absorption of light by biological tissue and also the scattering of light by biological tissue. And we are looking for some multidisciplinary approach for diagnostics and therapeutic applications. And to do that, we are working with people from physics and engineering field, life sciences, and also mainly on optics and photonics. I have several people in my lab right now, and mainly we are from molecular biology. We have clinical members and also animals from laboratory animal studies, electrical engineering, and biomedical engineering. And of course, we have collaborators from different cities and different universities all around Turkey. And we are trying to extend this collaboration with further people. And we've been lucky, and most of our research and our projects have been funded by several institutions, mainly from TÜBİTAK, Horizon and Horizon 2020 program, and TÜSEP. Right. Okay, so today I'm going to talk about superficial mucosal ablation, but we are working on different topics, which one of them is on laser scanning protocols and simulations of them, and the other one is artificial intelligence on GI tract applications and also radiology applications. And of course, we've been working on developing new laser systems using optical coherence tomography. And recently, this year, I believe, I presented again here another work on laser stimulation of peripheral nerves. But today, I'm going to talk about the importance of superficial coagulation and fiber probe design for this application and some Monte Carlo based simulation engines we did. And this work has been done by my PhD student, Merve Türker Burhan. But I just want to step back and try to understand clearly that what does superficial mean. It is in, if I double check the literature and see the late Latin word superficies, and in this word is just composed of two verbs, super and face. Super, obviously, you know one meaning of it, but there's another meaning, and this is above in this case. And face, of course, in some cases, as in here, the word for face means form or shape. So we are looking for the surfaces of the shapes. And in this case, it's going to be the biological tissues. So if our application site is in biological tissues or clinical field, I just need to double check what the constitution of tissues, organs, and organ systems, of course. So cells constitute the tissues and tissue structures constitute the organs, and organs constitute the system, organ system, and then this keeps going to the organism. And in our particular application site, I need to go back and see the esophagus is composed of several tissue layers. And the main tissue layers are mucosa, submucosa, and muscles, of course. But so why we are so curious about superficial coagulation in this particular case? So if I go and see, you will find that in some cases, superficial abnormal tissues that may spread to deeper tissue structures over time. In esophagus or in gastrointestinal tract disease, particularly, such as esophageal cancer or colon cancer or rectal cancer, can be caused by precancer superficial mucosal lesions and may then spread to tissue structures in time. So before penetrating deeper tissue structures, somehow if you find a way to treat this superficial abnormal tissues, that will be an important step before furthering in this disease. So Barrett's esophagus is one of the example of them. Barrett's esophagus was named by obviously Norman Barrett, and this precancer condition is the condition of lower esophagus. And mainly the normal stratified squamous epithelium of the lower esophagus replaced by columnar mucosa with intestinal specialized metaplasia. And it's mainly because of the inflammation in the lining of esophagus, majorly caused by GERD, gastroesophageal reflux disease. And the important thing with this disease is it is associated with esophageal adenocarcinoma, which is the 8th common incident cancer in the world. And if you go back and see the prevalence of this disease and the relation with the GERD, gastroesophageal reflux disease, it is varying from 1.3% to 4% in Europe and about 1.5% in Turkey. So what are the common approaches of therapy for this particular medical condition? The medication is one approach. It is reducing the acid production basically in stomach. And however, of course, it avoids further damage to the lining, but not necessarily to heal existing damage or to eradicate the abnormal tissue in superficial layers. So in some certain cases, there are being interventions, endoscopy therapy, and one of the intervention is the endoscopic mucosal resection. In this case, the surgeon inject the liquid, in most cases in saline, in the submucosal layer to lift the mucosal surface from the deeper structure and then resect the abnormal tissue. And in this case, it is mechanically resection. However, if this abnormal tissue structure spread it over the esophagus surface, the treatment requires several localized EMR, which is major limitation of evaluation for completeness of the therapy. And if we double check the other approach, we will come up with the endoscopic ablation therapies. In this case, there are several techniques that being used in the clinics. Argon plasma coagulation is one. RF radio ablation, radio frequency ablation. Most of you guys may heard and may be aware of it. Cryogen ablation, and of course laser ablation. However, there's also a problem in this approach. First thing is it is very hard to control the ablation depth, coagulation depth. So what's the problem with that? The main problem will be the damage of the healthy tissues instead of just ablate or coagulate the abnormal tissue. So that's the main problem. And the other problem is inadequate, not enough depth of therapeutic effect in some areas, leading to a presence of the BE, Barrett's esophagus, in mucosa. And there are several companies working on this and building new technologies to have comfort of the patient and also having efficient treatment. And this is one of the example. In this case, the probe is placed on surface in direct contact and applying RF ablation to deal with to ablate or eradicate the abnormal tissue on the surface. However, even from the image, you can see that thermal effect is beyond the superficial layers. And in our case, as in Barrett's esophagus problem, the abnormal tissue is mainly on the surface or the superficial layers. Well, what's the problem of doing treatment over in the deeper tissue structure? Or let me say that I think I'm explaining that later, but mainly your perforate or you're narrowing the organ, and also it starts bleeding. Those are the main problems of having uncontrolled or not mainly controlled therapy depth. So I need to double check again the basics of what I'm doing before start doing. And thermal ablation and coagulation of tissue is one main application, what we are, or the therapy approach that we are going to use. And that refers to destruction of tissue by extreme hyperthermia or hypothermia. And ablation is basically it may be hard to see in here, but you're just evaporate, or you're basically removing the tissue. Or in coagulation, you're basically killing the tissue or the cells, but the tissue structure is still on that area. But thermal effect will be deeper or wider than these application sites. So the problem in here is the applying fixed therapy depth. It may cause insufficient treatment depth, or it may need over treatment. And this problem may lead to perforation, bleeding, or organ narrowing. So our motivation is, despite some limitations and of laser therapy, laser ablation, or laser coagulation, the latest developments in fibers, fiber optics components, and diode laser technologies, the laser-induced photothermal coagulation may once again come to fore as closest approach, which means the superficial ablation. And necessary to develop the simulation engine, there is a necessity for that, because there is a matrix you need to simplify, which is the laser power or irradiance of the power, the laser diameter, and the application duration, which is the speed of scanning the surface. So there is a big matrix that you need to simplify to overcome these limitations. And one of the main thing in laser ablation, laser coagulation, is optical penetration depth. because not like the other electromagnetic radiation sources in this wavelength range, which is coming from deep UV or visible to near infrared range, we have optical penetration depth limitations. All right, so that's one of the main and critical point that we need to consider and think before developing our technologies in any kind in this biomedical applications. And the other thing is, of course, instead of just using regular light sources, we've been using basically lasers, which are the specialized laser sources that generates coherent light and narrow laser wavelengths. So we are able to control the light while we are shining the light through to the tissue, of course. But at the same time, the power of the laser or the light source you're using for this particular case can be lower than a regular light source. So what we have done so far on this to come up some solutions on this problem is one approach was developing a cone-shaped optical fiber to see if this fiber probe can give some solution on superficial mucosal layer ablation. So to come up with an idea, of course, we need to double check the current off-the-shelf technologies that we can find and we can have. And there are fiber tips that we would like to purchase, or we would like to double check how do they come up with their technology to beam shaping or shape the beam shining from the fiber. In our case, we thought that how about generating a cone-shaped fiber probe, which would mostly provide a tightly focused laser beam at closed range. And as you guys can see from this simulation, with the cone-shaped fiber tip, we will be able to have highly dense laser light in the closer surface of the tip, which will be well thing to try if we will be able to do superficial laser coagulation with low laser power. So in our case, the main approach with using a cone-shaped fiber tip, we would like to use low laser power for a high temperature rise in superficial tissue structure. But how are we going to do this shaping? All right, so how are we gonna focus the light as tight right on the tip of the fiber? So we came up with an idea that chemical etching might be a good approach, good technique to apply to the fiber tip to have this conic shape. This chemical approach, wet chemical etching, is very simple and very inexpensive technique. Easy to apply. However, you have to be very careful because you're using hydrofluoric acid, which is very dangerous, but still, as far as we know, there is a chemical reaction between hydrofluoric acid and fused silica. By using this phenomena, we will be able to etch the cladding before the core. And that's how we will be able to do selective etching with generation of concave or conic fiber tip. So this is a close range picture of the tip that we developed by applying this chemical etching to the single mode fiber, regular fiber, optical fiber. And this will be, and we tried several of those fiber probes in the tissue to see if we will be able to have this effect, what we are looking for. As I said, the probe and the approach, the tip of the fiber or the approach of fiber was developed basically in our case. But what laser we are going to use in our application? So if we double check the contents of the human body, the human body is mainly like, let's say 60 to 65% of water. So water is the main chromophore, or the material that we shoot for in laser ablations. Okay, so that's why this figure shows the absorption coefficient of water is a function of laser wavelengths. In our wavelength, the optical, which was 1505 nanometer, which is a very typical telecom wavelength, and the optical penetration depth was about 600 micrometer to between the 600 micrometer to 1 millimeter, which is critical range for superficial ablation. If you remember, the submucosal layer was about 1 millimeter depth. So we have double checks, right? First, the tightly focusing of light to the surface, and the second thing is the optical, the laser wavelength, which gives us the limiting optical penetration depth. So we have two controls to have superficial ablation or coagulation. So we set up a quick ex vivo tissue studies here. We built our probes, and of course we would like to scan the surface of the tissue. So we need to have some highly controlled motorized stage, and we use thermal cameras to measure the temperature of the surface, and our laser was there. We just purchased the chip, and we just it was not commercially available a laser, but the chip was of course commercially available. So we purchased the chip, and then we built our basically laser system there, and that was giving us the wavelength that we were looking for. So this, so we applied several studies in this case on ex vivo tissue. Ex vivo means a tissue extracted from an dead animal. In our case, it was sheep model. Okay, which was very easy to find, and we have the access to have the sheep, and also the anatomical. When you double check the anatomical structure of the sheep esophagus, we have big or almost similar structures between the human and sheep esophagus. In this case, we used very spatial staining. So in biomedical optics or biomedical engineering field, we are developing the system, and also we need to double check. We need to check that if we applied our laser ablation or laser coagulation in the correct way, there is a one key and golden standard, which is histology analysis. So in this case, we used nitroblue tetrazone chloride, which is very critical and very well working staining, rather than using a regular staining models. In this case, the I don't know if you guys can see, but the healthy part, which means not thermally damaged part, will be stained, will be painted by blue. But if there is a thermal damage in the tissue, it will be painted by only pink. So it will be very crystal clear difference between the thermally damaged and non-thermally damaged tissue layers. All right. I'm not pretty sure you guys can see in here, but you guys can of course welcome to double check our paper and see the high quality images of them. And of course we did several laser laser power range and surface scanning range, and it was perfectly fitting with the simulations that we applied, which was Monte Carlo based simulations. I will explain how did we do it in later slides. But with this result, we will be able to say, all right, cone-shaped fiber probes will help us, will give us the platform or the basic background for low power, for superficial ablation with low power laser radiation. there are problems with that approach, and I will come up with come that point later. So we've been working on this with several approaches. In another approach, we developed a simulation engine to understand how we can optimize or how we can control the laser parameters in an efficient way. So laser parameters are also very critical in ablation or coagulation, because in this technique, of course, you're basically rising the temperature of tissue. You're basically rising the temperature to a certain level. In protein structures, you're damaging the tissue in basically above 65 Celsius because of the protein structures again. However, how long do you apply the laser radiation is also a critical point. And there are several approaches, CW, continuous wave laser radiation, or pulse laser radiations to control this duration time. However, the pulse laser systems are quite expensive. So in our case, we are basically using for CW lasers, which may not be very suitable for a highly controlled ablation, because you're just applying the laser radiation and rising the temperature over and over again in time. But with the pulse lasers, you have some control. You're giving up the tissue some time to cool down, and which will give you better control on ablation surfaces. But if you have some engines, simulation engines doing a calculation for you, the correct timing and the laser irradiance, it will be also this highly controlled ablation will be also possible with using the continuous wave lasers. However, there is a very complicated matrix that you need to simplify. The matrix is of the laser irradiance, is composed of laser irradiance, beam diameter, and surface scanning, because the lesions or the abnormal tissue on the surface will not be localized. It will be spread over. So you have to scan the surface of the tissue with the laser to ablate or to coagulate the abnormal tissue. So of course, to build the engine, the simulation engine, we have to go back and recheck this phenomenal laser tissue interactions and the modes of these laser tissue interactions, and from this we will be able to see the first the reflection, of course, and also the scatterings. And in each scattering steps there is absorption event. So by using this, we will be able to simulate the laser tissue interaction. We were not the first people doing this. Monte Carlo is one technique, and it's working very well. So we basically use the technique to building our own engine, which has 4 modules in it. So this is basically the flow chart of our simulation here. This part is Monte Carlo simulation, so that basically defines the photon wave distribution in the tissue. So you're shining the light to the tissue, and with that laser tissue interaction, of the photons will be distributed all over the surface and within the tissue. So how are you gonna model this? So this is very well approach, and it's also the code of this Monte Carlo simulations is also available out there in internet. You can have. So you're launching the photon package to the surface and calculating the step size. So how big steps the photons will do in the tissue, and then in this case the system will check did it hit to the boundaries between the air and the tissue, and also tissue layers. And then in this layer, in this step, is there any absorption, or it is just scattering? So the photon will be absorbed by tissue, or it will be scattered to the different point. That's what it's gonna check. And if the weight of that single photon will be enough to survive to the next step, what's going to be on the next step? Is it another scattering or absorption? So this will be done millions of times. Okay, so we are sending basically a million of photons, and it is calculating this over and over again within million of iterations. And at the end, you are having some distribution of this photon weight, right? By using this photon weight, we convolve and normalize and interpolate this data, all right? So basically in here, we are adding our laser beam diameters. So we know the photon distribution, of course, but the critical thing in here is I forgot to mention, we are defining the tissue size, all right, the mesh size, and also wavelength dependent optical parameters, which are the isotropic factor, absorption coefficient, and scattering coefficient. After we have our photon distribution within the tissue, photon weight distribution within the tissue, we are basically convolve again the normalized and interpolate the data to have the Gaussian beam profile, basically, all right? And we are adding the laser beam diameters in this case here. From that, we are converting the photon weight distribution to the heat, because that's what we are doing basically, right? We are rising the temperature, so we are increasing the temperature by heating. So how do we do that? We are shining the light, and that light or the photons absorbed by the tissue, and with this absorption, the energy converts to the heat, right? So that's what we are doing, and in this step right here, we are generating the heat source generation. We are applying our speed in here. So if we want to scan the surface with this laser source, what will be the speed of scanning? So the speed of scanning will be added in this right in this corner, and then applying bioheat transfer equations, because by having the heat generation heat source will not be enough. There is a specific equations to understand or to calculate what's going on in biological tissue with that heat source. Finally, we convert this profile to, at the end, temperature profile, all right? And from that temperature profile, we are calculating the photothermal effect on the surface. And this all steps was done by my molecular biology, done by my student coming from molecular biology background, and she was graduated from this university. All right, so she didn't have an idea about physics and of course basic physics, but like laser tissue interactions, photon distributions, absorption coefficient, but she learned it and she managed how to build this entire system. All right, that's impressive. I had to note that here. And of course, again, we need to go back and double check our optical penetration depth again here. And since we have already the system running and working well, we decide to use the same laser system. But the critical point in here, and still missing, still there is a huge research going on in this side, is the optical properties and thermal properties of that particular tissue. It is too hard. Believe me, it is very hard to find those parameters. We've been doing this on the literature research over and over again over months to find the correct or the closest optical properties and thermal properties, because even if your model is perfect running, without knowing the correct optical parameters and thermal parameters, your calculation will be missed. And that you cannot fix it easily. Either you have to have a certain setup to measure the optical parameters by yourself in your laboratory and thermal properties of it, or you're gonna go and dig all around the literature and find the correct tissues. And the problem in here is, since we are working in the layers of tissue, in this case esophagus tissue, but layers, mucosal layer, submucosal layer, muscles, nobody work on it. That's the problem. So we are basically looking for the closest tissues and try to manage that will be correct spot. So this is still missing part. And why people are not working on it? Because the two-sphere, as everybody knows, two-sphere setup is not very convenient for small tissue layers. So if you're looking at the optical properties or thermal properties of a bulk, a big tissue, there is no problem. But if you shrink it, or if you're coming to the layer level, it will be very hard for that two-sphere setup to measure the correct optical properties. So that was the main issue for us. Instead of building the entire code and the algorithm, this took long time for us to find out the properties, optical properties and thermal properties, and we extract them from the literature. So, so of course, this simulation works in time and basically because we are at the same time scanning the surface, and we double check for different laser wavelengths, for different laser powers, and basically irradiance. Irradiance is the critical thing in here because of the diameter of the beam, and also we ran this in different surface scanning speeds. Again, we had our ex vivo tissue set up. In this case, we had to use the heater to heat up the ex vivo tissue to the body temperature, which was 37 degrees Celsius, and we used thermal cameras and digital cameras to see better what's going on the surface, because after we are applying the coagulation, laser coagulation, the surface is whitening. We call this whitening phenomena, all right? So surface changed the color. And we analyzed our probe. This time we are using regular probe. It's not cone-shaped probe, fiber probe. And we double check the laser powers, the wavelength of light, and the diameter of the beam. So of course, in calculating the irradiance, we need to find the area of the light. But since it is moving, we are scanning the surface. It is not just a single spot, which will be Gaussian. In this case, it is moving. So we are basically find a way to find the correct area to realize the irradiance of the light. So we came up with an idea that if it is moving in same speed, a constant speed over the surface, it will generate the small squares over the surface. All right. And we assume that our laser is perfectly Gaussian, which is because we are using a regular single mode fiber with a perfect narrow line width laser. And we decide to have this very basic square idea. So since the laser is moving over the surface, it's generating, let's say, the pixels or the squares over the surface, and that will be our smallest area, smallest pixel, as I can say. And then we were able to calculate the irradiance as the damage area on the on the end within the surface, the damaged area is a function of irradiance, laser power over the area, effect area, and the speed of the laser that we are scanning over the surface. But we need to validate these simulations, of course, and we applied this to ex vivo studies again, and again in this case it was sheep model. So in here we didn't apply the previous staining. All right, that staining was pretty expensive. All right, so it is not easy to find, and it's not very easy to apply to the tissue. There are some certain protocols that you need to follow. So in this case, we had to use the H&E, which is standard staining model that you can easily find. However, we came up with an idea that what if we do the imaging with bright field microscopy and also dark field microscopy. So dark field microscopy, I will give this details later, maybe in another talk. But in dark field microscopy, main difference will be the background is darker, black, basically, in dark field microscopy. In bright field microscopy, the background is white. But this has given us different colors, and we didn't color it. Same sample, paint is stained with H&E. We're using exactly the same microscopy, but just applying the black background or dark field imaging, we've been seeing some different colors as a function of thickness of the tissue. So if it is coagulated, it is thick, so it doesn't, the light cannot transmit it through that thick area, so it's basically seen black. Or green or different colors will be defined by tissue to the camera as a function of the thickness of the tissue, which was very cool because that will give us another way of calculating or measuring the damage area for our case. And these are the simulations results also we add. And we did very simple approach here, the color subtraction approach. So we have bright field data, we have dark field microscopy data, and we basically subtract those two data from each other. And that was giving us very cool and very defined image that will be easy for us to analyze which area we actually coagulate and what is the depth of the coagulation. It was very simple and very effective for our case. Of course, my student was very curious and she didn't want to stop in that point. She did the electron microscope imaging as well to understand in molecular or at least the very high definition level of the damage in those tissues to understand if our simulations are working well or not. And at the end, of course, this data is generated by our simulations, and we will be only applied our ex vivo studies in certain areas since our laser is not producing that high powers and we didn't have that resources to cover the entire parameters. But that was enough for us to compare our simulation results and the experimental results. In this case, we would like to, instead of just comparing the results in terms of the damage area, we would like to have also the energy, because heat is basically energy and we are applying laser energy. So, or the tissue is converting the laser energy to heat, right? So we would like to have the comparison in energy. So flux is main in comparison, that will be the joule per the area. So what will be the area in this case, or the flux, since we had that small squares approach to find the correct area, we applied it here along the way, since we did, so I'm sorry, we did very long scannings over the surface to do the coagulation. We applied this squares approach along the way and calculated the flux, and we compared the damage area as a function of flux, the energy density we applied. So this orange line show us the experimental data, and the dashed line show us the simulations, and it was almost like matching each other with a high degree. So I'd like to conclude here, and what I can conclude here is photothermal coagulation technique can be enough respond to needs of superficial treatments in GI tract. And this technique can be reassessed with advances in optical imaging, fiber optic components, and diode laser technologies at telecommunication wavelength range, which was 1.5 micron to 1.5 micron here. A Monte Carlo based simulation engine that we built can be a valuable tool to optimize the photothermal coagulation technique variables to eradicate superficial abnormal tissue structures. Fiber probe approach with further development, of course, may hold promise for endoscopic approach interventions. However, as you guys can understand and tell me that the tip of the fiber is super fragile, all right? So in real life, it will be too hard to use it. And right now we are working on another approach using this or comprehensively cover all those findings in one endoscopic approach and device. We are currently working on that, and we are almost done to developing that endoscopic device that we've been working last 2 years, 3 years. And I didn't want to present that data here today, since it is still on that publication level. Even though we applied for patent for that approach next year, if you guys invite me again, I would like to present that technology. So that's the conclusion we had. A better fiber probe design we may need to have, and right now we are working on that. So of course, I would like to thank our funding sources in this particular case, and I would like to have your questions and try to answer them. Thank you.
Any question?
How does the dimension R in your side of your square or the diameter of your circles compare with beam parameters? Like 1 over e squared?
Oh, it was 1 over e squared. The diameter we account in our calculation was 1 over e squared, because in imaging or in calculations of resolution in imaging, optical imaging, 1 over E or full width half max is critical, but in ablation, tissue sees the entire laser power, you know, like laser energy. So that's why we account the 1 over E squared in our beam diameter calculations.
Well, thank you very much for that great talk. I'm quite sure that each and every one here would love to hear the next comes next year's talks at IZTECH. So you're basically using the thermal degradation process.
That's true.
Would it be possible to start that photocatalytically? I mean, just ignore the thermal effects, but do the degradation through photocatalysis.
That will be.
Maybe that cannot be by laser induced, but
that will be also very specific and very good approach for superficial ablations applications. I never thought that. That will be possible, and it will be easier as well instead of doing those too many things. And
unexpected outcomes.
Sure.
May increase or reduce.
I don't know, but it has potential. I never thought that before. That will be a cool thing to consider it one more time. Thanks for that.
Thank you so much.
Thanks.
Dr. Serhat.
Thanks so much, guys.
Just to give a brief bio, Dr. Serhat graduated from Middle East in 2007, BS. And,
yes. It has to be at the beginning, but
yeah,
we had a technical issue here, so
yeah.
Okay.
And MS in Koç University in 2007, and 2012 he did his PhD in University of Northern.
Let's go back to that.
And then he joined the Harvard Medical School in 2000. I don't know when. 2004. Yeah.
So right here, 2005 Middle East Technical University, 2007 Koç University, my master degrees, PhD in University of North Carolina in Charlotte. There was a joint program, and that was in fact affect me a lot going further on biomedical optics, and we did cool medical applications with the collaboration in Johns Hopkins Medical School, and then I worked on Harvard Medical School for optical coherence tomography imaging.
And he's currently working in 9 Eylül University.
Yeah, I'm currently in 9 Eylül University, and also I'm working in Izmir Biomedicine and Genome Center.
So maybe if you have any question, you may
Sure.
visit it
Just
anytime.
Google me, or you're welcome to come and visit the laboratory and see our infrastructure and see the equipments and meet the guys in my laboratory. They would love to answer your questions for their particular projects. As I said, we have several different projects on biomedical optics.
Thank you so much.
Thanks for having me again.
Hello.
Hello. I'm
Okay.
here.
Great.
Here.
Thank you so much again for accepting to give us a webinar for this great presentation. I'm going to first start to introduce you, and then I will give it to you all the control, and you can start the presentation. Professor Wim Bogaerts, he is from IMEC and Ghent University. He is currently a professor in Ghent University. He is the driver behind the build-up of IMEC silicon photonics technology, and in parallel, he started developing design automation tools to implement complex silicon photonics circuit. In 2014, he co-founded Luceda Photonics, bringing the design tool IPKIS to the market, and we already know IPKIS is one of the biggest tools with the numerical that we use to design the photonic chip. Today, Professor Wim Bogaerts will present programmable photonic chips. Professor Wim, it's all yours. Thank you so much.
All right, thank you. I assume you can see my slides.
Yes, we can see your slide.
And now you can see me as well, I hope.
Yes, of course.
Hello. All right, nice to be here virtually, unfortunately. I hope there will be some opportunity in the future to visit Izmir as well in person. So I'm going to talk about programmable photonics, but maybe a quick introduction, not just of myself, because you made a good introduction of that. This is probably quite small, but it gives a quick overview of the group I'm in. I'm just a part of one of the professors in a group of 12 other professors, so that's a fairly large research group. Our main focus is photonics, so we're part of Ghent University. We're also part of IMEC, and we try to make or build photonic systems on a chip. And most importantly, we try to do that with the technology called silicon photonics. But in parallel, we've also developed integration technologies for a lot of different material systems like 3-5 semiconductors onto silicon. And in terms of applications, we're an engineering group. We're not a fundamental science group, so we're looking very much towards applications. We started out as a telecom datacom group, but nowadays we're very diverse into sensors, biomedical technology, etc. Now, as part of Ghent University, which is a city that you should definitely try to visit in the future, because it's really a wonderful city with a wonderful medieval city center, but it's also a very strong educational hub. And so over the past years, we've established a master program in silicon photonics, in photonics engineering, which among others teaches silicon photonics, but which is a full-fledged master program. So if any of you are interested in doing a master or another master in photonics, definitely consider Ghent. We partnered for a master program with the University of Brussels as well. So it's a quite elaborate 2-year curriculum with a very good balance between theory, real hands-on training in labs, and scientific research in the form of a thesis. So with a bit of luck, maybe we'll see each other in person in Ghent as well. So if you want to apply, there's just go to studyphotonics.com. There you can apply for Ghent University, and all the details on the program you'll also find there. So with that being said, switching from studying photonics to programmable photonics. Now, what about these two words? If we think about stuff that is programmable, you usually think about chips or calculators or computers or even toys, but usually not about photonics right away. While on the other hand, if you think about photonics, you think about manipulating light. And in many cases, you manipulate light on a small scale. And so programmable photonics, if we combine these two, we're talking about manipulating light using a software interface on a small scale. And the main reason to do that is because light contains information. And I think yesterday there was a talk from Sudip Shekhar as well, talking about using light to process information. And actually, a beam of light contains quite a bit of information. You have intensity profiles, the total power in the beam, the phase, the wavelength, the polarization, the modes. So there's a lot of different properties of light that you can manipulate that contain information. And the traditional way to do that, sorry, is to do that on a free space optical table with lenses and polarizers and spatial light modulators, etc. However, if you want to do that in a very complex way, you quickly end up with very complex setups, such as this particular setup, which was was demonstrated a couple of years ago, which is a 100-mode interferometer for quantum information processing, which works, but you can imagine what a pain it is to really configure this. So wouldn't it all be nice if you can take this entire setup and turn it into a single solid state device that fits on the surface of a chip? And putting things on chips has a lot of advantages. We know from electronics that if you do processing on a chip, sorry, you can increase complexity of circuits. Your performance goes up with a lot lower power consumption and a lot less material and a smaller form factor. So that's the whole idea behind silicon photonics, is that you basically bring photonics on a chip and you use the same silicon technology to get these high density photonic integrated circuits. The nice thing in addition to this is if you use silicon technology, you can process these chips in a CMOS fab. And that allows you in principle to make really complex functions, really complex chips at eventually a low cost and in high fabrication volumes. So you have these really nice scale advantages of silicon photonics that on one hand, you have large scale manufacturing. On the other hand, you have large scale integration. You can make these really small scale circuits that you can integrate in large quantities on a chip. And we've seen something like what you would call Moore's law for silicon photonics happening over the past few decades. The number of components on a silicon photonic circuit is exponentially increasing, and we're now running close to the 100,000 and with the direction of hitting 1 million in a couple of years. Now, this scale on the manufacturing scale also has an advantage. You can make really large quantities of silicon photonics chips. Just to give you an idea, what is a large quantity of a photonic chip or of a chip in general? Well, if you just take a very basic foundry, a 200 millimeter fab, not even the state-of-the-art foundries that make the best electronics today, but a somewhat older foundry. At full production scale, this runs about 36 million chips per month for the typical size of photonic transceivers. However, 36 million chips is quite a lot. It's actually more than 3 times the entire market of transceivers of 2021. And even if you go and have a very optimistic projection of 500 million chips market for 2025, that still amounts to a bit more than the production capacity of a single fab. So that's not a very hopeful perspective for large volumes. Essentially, in another metric, all the wafers that were started in a single month in a fab would roughly match the same number of silicon photonics wafers started in all 2021, and only half of that was roughly for production. So volumes like this are not sufficient to make sense for silicon photonics to really call it a large volume market. So where are we going to get all these other volumes? Well, we have to look a bit more diverse. Saying that photonic chips should only be used for communication is just like saying that electronics should only be used for calculators. But we also know that electronics today is used for a lot more things than just calculators, right? I mean, you find electronics everywhere. So can we think about the same thing for photonics? Are there other applications for photonics? Well, there's definitely plenty of applications for optics. So can we bring photonic chips towards these applications, to real products? And the fact that it has not happened today a lot in research, but not really in products. There's not a lot of photonic chips in products that are not related to communication. Why is that? Well, it's because developing a photonic chip is a very risky business. From a business perspective, it's costly. Just imagine that you want to build a data center optical link. You want to connect two ports together, so you need optical fibers and you need a transceiver at each end of the fiber. So, okay, let's design, fabricate, package, and test chips for transceivers. This is a traditional market for photonics, so this should be fairly trivial, right? So let's take a 100 gigabit transceiver. That's not state of the art, but okay, let's start with building a 100 gigabit per second transceiver. You can choose the architecture of using 4 parallel single mode fibers, so you have your light coming in, you have 4 modulators, and you send that light, modulated light, out through 4 fibers, and at the same time, your return signals are coming in to 4 other fibers and photodetectors. That's all nice and well, but this is only one way to build a transceiver. So depending if you want to follow the market, maybe you have to change and upgrade that link, and now you have to build an entirely new transceiver, for instance, for coherent communication. And you're taking the same 4 modulators and the same detectors, you just have to organize them in another circuit for an IQ modulator and a 90-degree hybrid coherent receiver. But it's the same building blocks. And it's similar as if you would want to use a wavelength division multiplexing link. Now you again need 4 modulators for your 4 lanes, but you now need to modulate, to multiplex the 4 wavelengths that you're using onto a single fiber and demultiplex these wavelengths when they're coming back out of a fiber. But again, 4 modulators, 4 detectors. But every time you want to build a new transceiver, you have to go through design, fabrication, package, test, and basically repeat this process multiple times until you get it right. And that is extremely costly. That takes you typically several years to get it right, to get something on the market. There's not many companies that have deep enough pockets to make this work. And now you should compare this to how things work in electronics. If you have a good idea for an electronic circuit for an application, and it's not super high end, it's not extremely crazy, then you basically just buy an FPGA or a digital signal processor or a microcontroller off the shelf. It arrives in your mailbox the day after, and you can start programming. And typically within a couple of weeks, you already have something that kind of works and that you can test with a customer. And only if you really need it, you design an ASIC to really go and optimize the functionality and the performance. But you already have customer feedback, typically within weeks or months. So, and this does not exist in photonics. Where is the photonic equivalent of an FPGA? A processor, a device that can essentially perform multiple functions that can be reconfigured with a software interface. So without having to buy new hardware, you can reconfigure it to perform different functions. So you can experiment with photonics in the same way that you can do with electronics. And such a processor would essentially have to do something very simple like this. It's easy to draw this in PowerPoint, of course. You have a photonic chip that has optical signals going in and out, but also high-speed electrical signals, because that's actually one of the things that photonics is pretty good at. But okay, this is very, very abstract, so let's make it a little bit less abstract and look at this overall picture where we have a photonic chip that has optical fiber interfaces. I've drawn grating couplers, but you could use other types of fiber interfaces. But your high-speed electrical interfaces are quite interesting because they're nothing more than high-speed modulators and high-speed detectors that immediately convert your electrical signal into an optical signal, process it optically on the chip, and then convert it back to electrical only at the very output. And everything else on the chip happens in the optical domain. Now, the magic block that makes everything work and that connects everything together to define a function is this big purple block in the middle, an all-to-all scatter matrix, which is programmable. Now, what does that mean? It means essentially that you have a circuit with ports, and a scatter matrix basically describes how each of these ports is coupled to one another. So you want a scatter matrix that's programmable. You want to be able to program how every port is coupled to every other port, not just zeros and ones, like all the power goes in or all the power goes somewhere else, but in any kind of distribution format, including control of the phase. So these scatter elements are complex numbers. There can also be frequency dependent. So you can basically use this device or this matrix as a filter system. And it's of course reciprocal. So you can use inputs and outputs, etc., mixed through one another. Now, if in the ideal situation that this circuit is lossless, that means that scatter matrix will be unitary. But it's a very difficult circuit to build. So let's make it a little bit more simple, and that should also go a bit back to things that you probably saw yesterday with Sudip's talk. Let's go to a circuit that has a defined set of input ports and a defined set of output ports. And we now only look at light propagating from left to right through the circuit. Can we build a programmable circuit that basically can couple any combination of input ports into any combination of output ports? And indeed, yes, that's possible. And the idea was already proposed almost 30 years ago. It's essentially a circuit that consists of beam splitters and phase shifters. And each beam splitter and phase shifter can be tuned, and you organize them in a triangular or diagonal way like this. And so this looks like a free space device. On a circuit, it would look a bit more like this. All your connections become waveguides. And basically every combination of beam splitters and phase shifters are what we call a 2x2 optical gate. It is essentially a waveguide component or a little waveguide circuit that takes two inputs, two outputs, and basically mixes them up. So you have tunable coupling, but also it controls the differential phase delay. So you have both amplitude and phase control. And such a circuit is described by a 2x2 unitary matrix. And essentially, if you cascade 2x2 unitary matrices, you can construct any unitary matrix. So how would you physically implement this on a circuit? Well, you need essentially two functions. You need control of the phase and you need control of the coupling. And in many cases, control of the coupling is done with a Mach-Zehnder interferometer. You basically split your light 50-50 over two arms. You control the differential phase, and then it controls constructive and destructive interference. So that gives you control of the coupling. You just need one other phase shifter somewhere else in that circuit to give you control of the phase. And that's it. And if you now take these gates and you organize them in this triangular fashion, you can construct any unitary matrix. You can also do it in other ways. You can do this kind of meshes, which were proposed by Clemens in 2016. But the functionality is very similar. You can basically now map any set of inputs to any set of outputs. And the first demonstration, physical demonstration of this kind of application or circuit was done in 2015 and by the University of Bristol, specifically targeted at quantum optic operations. 1 year later, we described the first, or demonstrated the first silicon photonic circuit with the same functionality. And even a year after that, there was already this circuit, which has not 4x4 inputs, but in this case, 26x26 modes that can be coupled together. Now, why would you build a circuit like that? What is actually the function of such a left to right circuit? Well, the interesting thing is that if you represent your input waves with a set of complex numbers, amplitude and phase, and your output waves the same, then what this circuit does is essentially just a matrix vector multiplication because it's a linear circuit. So you now, at the time that light needs to propagate from left to right through the circuit, you perform a matrix vector multiplication. And that is a very useful function because it's the basic function behind all kinds of pattern recognition, quantum optics, and neural network algorithms. So you now have a circuit that can perform this function essentially with zero static power consumption. It's essentially your light is just propagating through the circuit at a time that at very low latency, just the time that light needs to go from left to right. So it's not surprising that because these are this kind of crucial algorithms that most of the demonstrations of these circuits find their applications in quantum information processing, demonstrating quantum computing operations, such as, for instance, this demonstration from Quix last year, where they have a 20 mode, so 20x20 fully programmable interferometer circuit, like the one I showed you earlier. Other applications that are typically targeted are accelerators for AI, like for instance, by Light Intelligence or different universities in the world. However, it does not really address the problem that we started with. All these circuits, they perform these flexible, programmable matrix vector multiplications, but they cannot do much else than that. They are still what you would call ASICs. They're application-specific circuits. They're programmable, but they can only do one trick. That's the matrix vector multiplication. They don't solve the problem for rapid prototyping that we wanted for our product development. So we still have to go back a little bit. These circuits are too limited. They are programmable, but they are too limited. They still separate your inputs and outputs in hard inputs and outputs. And you cannot really make flexible delays, which would give you filters. So if we wanted to go to circuits that have programmable delays that can also do optical feedback and wavelength filtering and dispersion engineering, we need to do something else. Because these are the kind of features that would allow us to process time signals, do integration differentiation, and do really programmable analog signal processing. So we have to go back to our original idea of, instead of having a left to right circuit, we need a fully programmable all-to-all scatter matrix. And again, the way to implement that was first proposed already quite some time ago, in 2015. Essentially, you take the same type of optical gate that we now know, but we organize them in loops. So now you have, instead of forward propagating light, you now have light that circulates. And the gates control how the coupling between all these circulating rings or loops is handled. And you can do that with square loops with 4 couplers on each side. You can do that with hexagonal loops with 6 of these gates on each side. But you still use exactly the same gates as we used before in our left to right meshes. And the nice thing is that you can do quite a lot of functionality just with configuring these gates. You can of course switch where light is going anywhere in your mesh from any port to any other port by just switching your gates from cross state to bar state. You can of course route multiple of these waves through the same mesh, and you even can very easily solve a common problem in photonic circuits, the problem of crossings. You just have to switch one of these gates from a bar state to a cross state, and you have a crossing. So you can also put these gates in partial coupling state, so you can use them as a splitter. And in the same way, you can use them as a combiner. And now this becomes interesting because what you see here is an interferometer. And if you make an interferometer with a delay, which you can very easily implement by just routing light through an extra path, you get an optical filter circuit. And for making filters, there's even an additional trick that such a recirculating mesh offers you, that is to make a loop, essentially a ring resonator, which gives you these very nice sharp resonances. So you can see that this mesh is much more flexible than the left to right, the forward-only meshes that I talked about earlier. This really allows you to loop and to make filters and to couple anything to anything. There are some constraints, though. If you want to make a Mach-Zehnder filter, you cannot make a Mach-Zehnder filter with any arbitrary delay length. You basically are limited to Mach-Zehnders with a fixed number of these unit lengths that you're using in your mesh. And the difference always needs to be a multiple of 2. The same holds for ring resonators. You can only make ring resonators with a minimum of 6 units, of course, because otherwise you cannot make a loop. But then the next one is 10, and then 12, 14, and 16, etc. So again, you can only make rings with fixed unit lengths, which gives you a kind of a limitation of the kind of filters that you can build, because the length of the ring, the length of the Mach-Zehnder, tells you what your free spectral range is going to be. And so that's basically the repetition of your filter in the spectral domain. So you can only make fixed sets of free spectral ranges. And if you want to make a filter with a large free spectral range, that means that you will need a very short unit length. So sharp bends, short phase shifters, compact splitters, dense packing, everything needs to be very compact. And that's kind of difficult to make. It puts quite some constraints on the type of gate, the type of phase shifters and tunable couplers that we want in our circuit. Essentially, we want very good gates that are compact, have a short optical length, low optical loss, low power consumption, preferably also a CMOS compatible drive voltage, can be fast, and have low crosstalk, both electrical and thermal crosstalk. And you need to be able to make many of those. And preferably, you want all of these also to work together with all the other functions in your photonic platform, like silicon photonics modulators and detectors. So the ideal optical gate has quite some constraints and conflicting requirements. So how do we make them? Well, there's a range of technologies that you can use, such as heaters, carriers, MEMS devices. You can do liquid crystals. You can do all kinds of different other materials like piezoelectrics, phase change materials, or Pockels effect materials. But that's a whole variation of devices or of technologies that you could use to make these phase shifters. And all have their advantages. Some are fast, some are slow, some are strong and some are weak, and some consume a lot of power and some consume very little power. So let's look at a couple of examples. And let's start with the technology that's used by most platforms today because it's so easy to implement: heaters. Essentially, waveguides, and especially silicon waveguides, are temperature sensitive. So if you put a metal resistor or a silicon resistor next to it, you run a current through that, what you get is a temperature increase and therefore a phase shift. And that's a very easy thing to do. And it's very easy to implement it in a technology platform like this. This is IMEX technology platform. You can have silicon heaters sitting next to the waveguide, or tungsten heaters sitting on top of the waveguide. And it's very easy to implement, and it's very easy to operate. You just have to run a current through it. And the only thing that really determines how efficient such a thermal tuner is the whole thermal environment. It's not really the optical properties of the materials. So basically, what you need to make an efficient heater is to make sure that as much heat of the heater ends up in the waveguide and not somewhere else, and that it cannot leak away. So you have to make your heater small, that everything is close together and insulated well. And this is some example, like a very compact heater where your heater is really, it's sitting in the same silicon as the waveguide even, so it's really close to the light. And if you then use techniques like undercutting, like removing the substrate underneath the heater so that the heat cannot leak away, or removing the backside, for instance, altogether by just drilling a hole or etching a hole in the backside, you get these heaters like this example who can be extremely efficient because they're basically just heating the material, the silicon where the light is, and not much else of the material. But still, even with all that engineering, heaters have a problem. They still need constant power consumption on the order of milliwatts per heater, and they still have some thermal crosstalk. If you heat one heater somewhere else close by, it will also feel the heat. So we need something better than just this. And so if we go back to our little table, or little graph here, there's a lot of different materials that we're researching in the group. I'm just going to cover two of those now very briefly. And the first is liquid crystals, which sounds like a bit of a weird material to use on a chip because it's a liquid. But okay, we know liquid crystals from displays. They're everywhere in our life today, and they're quite mature technology. And if you put a liquid crystal material around your waveguide, you get all these molecules, these long anisotropic molecules aligning along the line of the waveguide. But then if you apply an electric field, you can rotate these molecules to align with the electric field. So the mode, the optical field in the waveguide now sees a very different material because the molecules have rotated. And this is a very strong effect because these materials are really very anisotropic. The only problem is that you have to integrate these materials in a photonic chip. And typically your waveguides are sitting here at the bottom of this stack, covered by metal and dielectric. So you first need to open up this area locally to put your materials there, and then you need to get your liquid crystals in, which can be quite tricky. But for instance, techniques like inkjet printing now allow you to do this. And then inside this cavity, how would you actually make a phase shifter out of that? Well, there's different geometries that are possible, but one of the geometries that could be very useful is the one shown here, where you have a waveguide on the left and then a thin rail of silicon sitting on the right. So if you apply a voltage over the waveguide and the rail of silicon, you can reorient your liquid crystal. And this is quite useful because you have liquid crystal sitting right next to the waveguide where the light can still feel it, and it's a narrow gap, so you don't need a very strong electric field. So we actually tried that out, and here you see a chip with liquid crystal deposited using an inkjet printing technique. Here you see one of those cavities, a larger one without liquid crystal. And so we can apply voltages through these pads here, and the circuit, the optical circuit itself, is just a very simple Mach-Zehnder interferometer. So you basically can see from the shift of the fringes of the Mach-Zehnder interferometer how much phase shift we can get, and we see that with a 5-volt voltage we can already shift it more than 2 pi over more than 2 pi in phase. That's a lot for 5 volts and a length of only 100 micrometers long. So this is definitely a very promising technology for phase shifting. But of course, it has the complication that you now have liquids on your chip, which is not something that you always want. So are there any other alternatives? Well, yes, obviously. Let's look at the MEMS, which is something that we have been working on over the past 5 years now with quite some success. It's actually quite easy to make a MEMS tunable coupler. You take 2 waveguides. If they're close together, they couple. If you pull them apart using a mechanical system, they stop coupling. And you can do the same thing for a phase shifter. You have a waveguide. If you have a thin rail of silicon sitting next to it, and you pull that rail closer or farther away from the waveguide, it acts as a perturbation and induces a phase shift. But again, as with the liquid crystals, you have the problem that you need to make these devices, these movable devices, in the same platform as already your other components like modulators and detectors. So we're back to our question, what do we do now with our photonic platform? So first, we added an alumina layer as a protection. So that's the light blue layer to make sure that for every MEMS, all the MEMS processing that we do, we're not attacking the existing structures. And then we use a vapor HF etch, which is a very aggressive etch of hydrofluoric acid, to remove locally underneath the exposed areas the silicon dioxide. So now the exposed areas become freestanding. And this gives us essentially this kind of phase shifter. And you see the footprint here. It's only 60 by 40 micrometer, where your light can propagate from left to right through your phase shifter. The thin narrow beam of silicon can be moved, is suspended on these folded springs here, and when you pull them using when you pull on this shuttle using this comb drive actuator, you can now pull this beam further away from the waveguide and induce a phase shift. And if you put this whole structure inside a simulator, an electromechanical simulator, and then put it in an optical simulator, we expect a pi phase shift for a 30-volt actuation. In reality, it turns out to work even better, and we already get our pi phase shift for a 20-volt actuation. Note that this is a high voltage compared to traditional CMOS voltages, but the device itself does not really consume static power because it's just an electrostatic device. You just charge a capacitor, discharge a capacitor. And the same principle of device you can also apply to tunable couplers. So if you have 2 identical waveguides sitting close together, and you have them basically sit close enough that all the light can couple from one waveguide to the other, if you now apply a voltage on this comb drive here, you're pulling one waveguide further in, which basically separates the waveguide, and now you're switching your device from a drop state to a pass state. And this is one example where you have such a suspended waveguide with indeed this tunable coupling functionality. So we have the tunable couplers and the phase shifters, which actually allows us to make these optical gates and these programmable circuits. So this is an example of one unit cell of such a programmable circuit. So you have 3 tunable couplers here and 3 phase shifters, and then you have another one sitting over there, and then you connect all of these together with waveguides to get a much larger circuit of many hexagonal cells together. Now, there's one challenge that we have to see here. You see all these devices, these are MEMS devices. They're all exposed. So if a little particle falls on the chip, they're basically broken. So they need to be protected. And as part of the project, the Morphic project that we developed this in, basically KTH, our partner, developed this hermetic sealing process, which put a silicon lid on top of the MEMS devices and locally for all the MEMS devices in the same chip. And this is done on a wafer scale process. So it's a very, very parallel process, but all the MEMS devices essentially go from being exposed to being fully covered. And the lids are quite thin, so they only stick out a little bit, and you still have access to all your metal bond pads for your electrical contacting and your grating couplers for your optical measurements. Okay, we now have a couple of solutions, potential solutions for good optical gates. But of course, we need a lot of those on the same chip. And I already showed that these MEMS circuits, we can indeed integrate them in large circuits. But still, all of these devices need to have optical and electrical interfaces. They need to have a driver circuit that controls them. We need to monitor where the light is on the chip, and we need algorithms to control all these building blocks. So that's a lot of extra functions just to make these programmable photonics work. It's more than just making good gates. So every gate, first of all, needs its electrical driving circuit. So you need some digital to analog converter that drives the phase shifters and the tunable couplers. And then you need some digital circuitry that controls everything and that basically manages everything together. So it also means that for each of these phase shifts and tunable couplers, you need a wire going out of your chip. And that's a lot. If you have 1,000 of these tunable elements, you need 1,000 wires of chip. And the ideal solution, of course, would be if you would have a nice driver electronic circuit that's specifically designed for your photonics and that you just flip chip or 3D stack on top of your photonic circuit. And that's the ultimate solution, but it's a very costly solution to develop. I mean, it takes a lot of time to develop a good driver circuit, and to have it fabricated takes a lot of money. Even better would be if you have the electronics sitting really right inside your photonics chip. That's even more complicated, more difficult to design, but once you get it right, it might be a very powerful solution, but it's a very costly solution as well. So for every short-term development, you'd rather go to a packaging-based approach like wire bonding or flip chipping or interposers. For instance, like this very spectacular demonstration by Quix, which requires like 3,000 wire bonding connections just to connect their 20 by 20 mode optical processor. This is another large-scale example of such a programmable photonic. Well, it's a LiDAR. It's programmable, but it's not generic programmable. But it requires 8,000 controls. And in this case, everything was done on a very large silicon photonic chip with then a set of flip-chipped electronic driver circuits, each controlling 1,000 elements at the same time onto that silicon photonics chip, which is a very spectacular demonstration, but also very costly to develop. So how do we control something like this? We have this large circuit, which in total requires close to 1,000 electrical wires. What did we come up with for this circuit? Well, the solution that we came up with looks like this. This is actually the full chip. Not everything is our programmable circuits, but there's a lot of other designs there as well. And we designed essentially a standard grid that fits perfectly onto a large-scale interposer. And this is really a large-scale interposer. It routes over 3,000 connections to the outside world with a 21-layer interconnects, 21 layers of interconnects. And if you look at the actual device here, so you see this grid. You also see some connections for high-speed wires, for the high-speed modulators and detectors. And this was developed by Tyndall together with Kyocera to basically couple these really complex circuits to the outside world. On the side of the chip, you have these little pads here which have 150 micrometer pitch. On the other side, if you just look at on the back side of this interposer, the spacing is much larger, and now we're looking at spacings of 1 millimeter between individual pins, which is compatible with printed circuit boards. So you can put this kind of interposer on a printed circuit board and then wire it to whatever connections that you want to control your circuit. Now, once you have the circuit, of course, you need the electronic driver circuits as well to make everything work. So specifically for the MEMS devices, we developed driver boards that control 64 channels each, and you can stack up to 12 of these boards in cascade to control very large circuits. And everything is connected together through an Ethernet system, which you can then control through software, which not only helps you to make the circuit layout and the circuit simulation and the hardware control, but also can integrate mesh configuration and feedback routines to basically control the mesh to make sure that it does exactly what you want. And these controls are not that trivial, because you basically now need to monitor what is inside your circuit. You need to read that out and then make sense of it, either using an analog control loop or a digital control loop or a software control loop, to adjust all the phases and tunable coupling ratios of your device, of every device on your chip. Now, that's more complicated than it seems, because essentially every device is slightly different. This is an analog circuit. It's not a digital circuit. So everything needs to be very precisely controlled. Luckily, there are some techniques that can help you. For instance, let's take a very, very simple example. Let's assume we have one optical gate. It consists of a phase shifter and a tunable coupler. And we want to configure this optical gate to couple all the light to the bottom port, to output port 2. Now, you can either very carefully characterize your phase shifter and your coupler and then set the values that you need to get that configuration. But you can also do it in a smarter way, which does not require any calibration or any calculation. No, you basically just place a monitor detector right after port 1. And now you basically use that detector to minimize the power in port 1 by tuning your phase shifter. And so that basically turns the contributions that go to port 1 into destructive interference, which means that all the light, or at least the light, is minimized and goes to port 2. However, this is not enough. You still need a second feedback loop on your coupler to make sure that the two contributions balance out perfectly in port 1 and basically fully cancel each other out, which means that you can fully eliminate all the light that goes into the detector. And by definition, because the light cannot go anywhere else, it ends up in output port 2. And this is just one gate, but you can cascade such gates with detectors in a whole line. And you can, for instance, now use this to optimize the light of 4 inputs into output port 4 by just using these feedback loops on these different detectors one by one in sequence to cancel out the light in output port 1, then in output port 2, and finally in output port 3. So, and these feedback loops can all run in parallel. They don't have to be run sequentially. They can be run in parallel, and you can sequentially optimize what is going on, where the light is going in this sequence of gates. And if you now make your detectors not fully absorbing, but just slightly absorbing, so most of the light goes through, you can basically now put a second row and a third row behind this circuit to build this kind of forward-only circuit that we discussed earlier. But you can use similar algorithms to connect these circuits into loops. Just some example, this is an example where we use this kind of feedback system to configure the circuit with an adaptive algorithm into a 1x4 splitter. So basically 1 input, 4 equal outputs. And it just balances out the circuit automatically without performing real calibration or calculation on the devices. That gives you basically an entirely new way of defining functionality. Instead of before, we use photonic circuits, which basically consists of a full custom geometric design, or even photonic circuits based on standard building blocks like nowadays used a lot in silicon photonics, based on a PDK, a design kit. Now we don't have to design a circuit. We have our circuit, it's there. But we need to configure all the ports. We need to basically set the state of all the ports in such a way that the circuit, the light goes where we want it to go, and that it performs exactly as these custom designed circuits, which we originally designed. So it basically shows that with these programmable photonics, we now get a whole new set of ways of defining functionality. You can do programming routines which do not exist yet to extract functionality from an application-specific circuit and mimic it into a programmable circuit. But then basically that also needs a control strategy and maybe later a way to bring that programming back to your application-specific circuit. So you need algorithms to do that. And so we started building reconfiguration algorithms based on graphs. So we actually developed a graph representation of these photonic circuits. And it's a bit more complicated than the one at the top. Eventually, it looks like this. But once you have a good graph representation, you can use these algorithms, which are used for FPGAs or for network configuration, to do routing, and even routing with collision avoidance and congestion negotiation, until you get the configuration you want. You can also use it for more difficult problems like distribution problems, where you can have different penalties. For instance, here we wanted to minimize the number of blocks that we used, while here we wanted to minimize the power in the waveguide. So we split up as quickly as possible to reduce, for instance, nonlinear losses as to photon absorption. So I hope that this gives you an idea that actually building these programmable photonics, it's more than just a photonic chip. It's a photonics plus electronics, both analog and digital, and software algorithms to make everything work. So that eventually you can come up with something that looks a bit like this, like a kind of a Raspberry Pi for photonics, where you have inside your photonic and electronic chips, and then connected to the outside world with a fiber array and with high-speed connectors for your microwave functionality. And in parallel with the hardware, you would then have a software library that basically helps you control the feedback loops, the configurations, eventually a development kit, a programming kit, just like you can get with FPGAs or Arduinos or any technique, and any off-the-shelf microcontroller or FPGA. So you need this entire technology stack going all the way from the photonic chip all the way up to software development kits. Now, the good news is that there's already some of that out there. And this is an example from the company IZPHOTECH in Spain, which have actually recently demonstrated such a programmable photonic chip, which has 64 input and output ports. It's a box like this. It can be accessed over the internet, and you can basically remotely program the functionality of this tool for experimenting with it. So that would basically give you this kind of programmable photonic processor that allows you to do switching of light, to do splitting and filtering all together in one, essentially in one chip. Now, why is this important? Well, it allows you to make now all these functions that we started off at the beginning. Let's say that we want to make our programmable transceiver. Well, we can do that, but we can just route the modulators and the detectors together in such a way that we can now do all these programmable functions. So all these transceiver functions, 4 fibers in, 4 fibers out. But if we want to change our protocol to coherent communication, we just have to rewire the circuit. We just have to reprogram the connections for a coherent modulator, an IQ modulator, and then basically on the receiver side, a coherent receiver using a 90-degree hybrid. And we can tap off a little bit of laser light as our local oscillator. And the same thing we can do for wavelength division multiplexing, because we can now put 4 lasers at the input, and we can use ring resonators, which we program in the mesh to basically multiplex and eventually also demultiplex the signals coming from the receiver. And it doesn't stop with just making transceivers, of course. I mean, the whole idea is that you can do other things. You could make a bank of ring resonators to function as a spectrometer. Or you could operate it as a switch, connecting 8 fibers to 8 other fibers, for instance, by just rewiring how the light is going between all the fibers. So you see that there's a lot of possible functionality there and a lot of possible applications. And therefore, we can imagine that these programmable photonic circuits could find their way into data centers and for switches and transceivers, which are quite traditional applications, but also towards new communication-based applications, especially towards, for instance, access networks, fiber to the home, which can then be programmed inside a building to route the different signals to different subscribers, and even using the microwave functions to route signals to subscribers that have not yet switched to fiber. And because you have these fiber connections anyway, you can also use this to access the 5G infrastructure using radio over fiber communications. And communications is not the only thing. You have also, of course, all these ideas of using photonics for sensing, which today take a lot of time to develop, but with a programmable chip, you might be able to get much quicker development, for instance, for fiber Bragg rating sensors or for sensors in cars like automotive, including the very prominent sensors that we see today with LiDAR, for instance, to optical beamforming. Or, for instance, microwave radar processing for drones will be very lightweight. On top of that, you have this kind of sensor functions that you typically want to see in biomedicals, like blood analysis or optical coherence tomography in your dental office or for your eye surgeons. So it's a chip that, or these chips eventually could find their way in all these many applications. But does that make them the one chip to rule them all? Well, in a way, yes, because it can handle all these functions. It can combine microwave and optical. But on the other hand, no. Just like in electronics, these flexible chips can do a lot of things, but they're typically in large volumes quite expensive. They also have typically higher power consumption and higher optical losses in this case than a custom design chip. And so eventually for some applications, you will still require an ASIC. Now, there is some big advantage though in terms of cost. If you just think about developing a new product, you would basically, for a new product, need to develop a new chip for both the photonics and the electronics. And all those costs come to you, including the packaging costs that you need to build your product and assemble your product. So with a custom application-specific photonic IC, all the costs are with the same product developer. However, if you have generic photonic ICs, programmable chips, these could be provided by a chipset supplier, and who's not just supplying you, but also supplying a lot of other customers. So they basically can make these chips in larger volumes and share the cost of these chips over many customers. And that basically gives you a major cost advantage because the chips can now become a lot cheaper for you to use. And they also give you an additional advantage in terms of time. Instead of going from your new wafers to your shiny new products, which takes you quite a lot of fabrication time. So you basically have to have your own wafers fabricated. That takes you at least 5 months, typically more than a year nowadays. And you need to develop the packaging and the programming, etc., to make it work. While with a generic programmable photonic chip, you would cut that supply chain in half. And now you have a lead time for your chips of only a few days because you're sourcing them from a supplier. So it gives you really a tremendous cost and time advantage in your programmable photonic circuits. The second advantage or major advantage economically for these programmable photonic circuits is that they can be upgraded. So you can basically, because everything is defined in software, you can basically use these circuits for different functions or add new functionality with over-the-air upgrades to your product. So that gives your product a longer lifetime. And because everything is also programmable, if something fails, you might be able to reroute your circuit to still function with through another path. But probably the biggest advantage of these programmable photonic circuits is the fact that you now have an electronics and software interface. And for every photonics engineer out there, there's 10 electronics engineers and 100 software engineers. So you suddenly have a community that is 100 times larger that can now do innovative, fancy new things with photons. And we don't know yet where that is going to end up with. There's going to be so many good ideas for applications, so many new sensors, new gadgets, new things where photonic chips will eventually find their way into the hands of the consumer. So that brings me to the end of my talk here. What I try to convey here is that programmable photonic chips, even though they're still in a very embryonic phase, can really become a game changer because they can completely change the ecosystem of how people innovate using photonic circuits. And it would enable rapid prototyping and development and open the door of photonics to many more applications than we find now today, because it lowers the cost and lowers the risk of developing applications. There's still some challenges, though. I mean, we need these very good optical gates, and we need to make them in very large quantities. They need to have very good yield, very low loss, very low power consumption. All the control electronics need to plug in there, and all the programming algorithms. That's an entirely new field that's still very, very early in its development. So there's a lot of new ideas that are needed there and new knowledge to program these circuits and to come up with clever algorithms. But the benefits could be immense. The faster prototyping, the lower adoption threshold, and the lower cost for low volume applications can make a huge difference in the adoption of photonics. And so with that, I want to end here. I just want to thank all my colleagues who in some way contributed to this presentation, also the funding agencies that helped me pay for all this research. And last but not least, I would definitely say, if you want to do a master in photonics, think about going to studyphotonics.com and apply for our wonderful master program in Ghent. Are there any questions?
Thank you so much. Any question? Actually, I have one question. How about when do you think we can get the CMOS photonics chip in the market? There are so many works or they've been done, but well, what is the prediction?
Well, you mean like a programmable photonic chip, or in general, what do you mean with CMOS photonics? Because that's a bit of a confusing name.
Yeah, not programmable, but the ASIC CMOS photonics.
So a silicon photonics with CMOS electronics sitting together on the same chip.
Yeah, but in the market.
In the market, it's a good
like
question.
The mass fabrication.
Well, actually, the answer would be 2012, because Luxtera's transceivers, first generation transceivers, really were a combination of CMOS and integrated photonics. They actually abandoned that approach for very good reasons, because the requirements for the CMOS and for the photonics are quite contradictory, and you're actually competing for the same floor space. CMOS transistors are quite small, need very uniform density, and the photonics basically disrupt all the design rules that you typically find in CMOS. That doesn't stop people from trying implemented it. Global Foundries, for instance, has a very good state-of-the-art silicon photonics process with integrated CMOS, which you can basically use today for multi-project wafer runs. And you can even, if you would have a product design, you could even have it fabricated in volume. So the technology is there. There's other work, like for instance, the work from Air Labs and Colorado Boulder and Boston University, etc., and MIT, using zero change CMOS. So basically trying to build photonics inside a CMOS chip and without changing the process, which works, but typically where the quality of the photonics is not at a very high level. So the waveguides are typically still quite lossy. But it works, and if you really want to integrate the photonics close to the electronics, you can. But like I said, it has quite a lot of trade-offs, and the only point where it really makes sense is if you need really high-speed drivers sitting really close to your photonic circuit, so that you minimize the capacitances and the resistances of the coupling between your photonics and your electronics. And so a process like Global Foundries process, or for instance, IHP in Germany, which combines BiCMOS with photonics, I think works for that. But in practice, all the other electronics, everything where you don't care too much about the capacitances between your photonics and your electronics, you would do in a different process, in a process that's much better suited for that. And then you integrate them with 3D stacking or flip chipping. So CMOS photonics, like really photonics and electronics in the same chip, in my opinion, is mostly going to remain a quite limited technology in terms of applications. Only the applications that can really leverage that technology to its maximum extent will be cost effective for that technology, because it's much more expensive than taking electronics and photonics in separate chips. Does that answer your question?
Yes, certainly. More than what I expected, actually. thank you so much. It was a great presentation.
My pleasure.
I hope you invite you maybe next year face to face. I guess at least maybe if you have a time for the next year, we would love to have you.
I would be delighted. I mean, it's
Okay.
the only difficulty is that there's so many nice places to travel to, and you have to make choices. So Izmir sounds great.
Well, we will promise it's one of the best places.
Yes, I'm looking forward to it.
Okay, thank you so much. I wish you have a great day.
Same to you, and enjoy the rest of the symposium.
Thank you so much.
Hello, welcome, Professor Zeltner. Can you hear me?
I can hear you. Can you hear me?
Yes, we can hear you and see you clearly.
Perfect.
Before your presentation, I'd like to introduce you to our audience shortly, and then you may start your presentation. We will start this section by the presentation of Dr. Richard Zeltner. He is a project leader and executive assistant at German laser manufacturer Menlo Systems, and he is a member of 2020 class of Optic Ambassador. Before he joining Menlo in 2019, he worked as a researcher at the Max Planck Institute of Science of Light in Germany. His PhD project evolved around optical trapping inside hollow core photonic crystal fiber, with a particular focus on developing novel optical sensors based on optical propelled microparticles. Today, I believe he's going to make a presentation about sensing using optically trapped microparticles. And his talk will include, he's going to introduce hollow core photonic crystal fiber as a platform for optical trapping in general, and he will discuss in detail how optically trapped microparticles inside these structures can be used for sensing applications. If you wish, you may start your presentation.
Yeah, thank you very much for this kind introduction. You should all see my screen now, right?
Yes, we can.
Perfect. So yeah, once again, thank you very much for the kind introduction, and also thank you very much for setting up this event on this day of photonics in the first place. And yeah, I'm very happy to be here. Once again, I'm Richard Zeltner. I'm working as a project leader and executive assistant at the German laser manufacturer Menlo Systems GmbH, and I'm a member of the Optical Ambassador class of 2022. And well, the title of my talk today will be Sensing Using Microparticles Trapped Inside Hollow Core Photonic Crystal Fiber. Before I start with the actual content of the talk, I would like to actually acknowledge the people that were involved in this work, because usually if you do it at the end of the talks, this is usually done in a very rushed way and sometimes even forgotten. So all the work that I will present here has been carried out at the Max Planck Institute for the Science of Light and the University of Erlangen-Nuremberg, and in the division of Professor Philip Russell, who was also my supervisor for my PhD. Both Taimin Oysa and Sheng-Lung, who were my supervisors to my PhD, were very much involved in the work, as well as Dimitri Bikov and Ricardo Panetta, two PhD students with whom I worked closely together on some of the projects that I will present. So, well, I've mentioned initially that I'm working now in a laser manufacturer, so I would like to give you some perspective of why I'm actually qualified, or thinking I'm qualified to give a scientific talk on this topic of particle trapping. So I started my own studies in 2009, actually in a program called Integrated Life Science, which was an interdisciplinary program in which I was trained in bioinformatics as classical biology, bioinformatics and biostatistics, but also biophysics. And during the course of these biophysical studies, I came across photonics as a tool for doing biomedical research. And this sparked a quite broad interest in the whole field of photonics in me. So I joined the division of Professor Gerd Leux at the MPL in the Max Planck Institute, in Erlangen, where I've been working on sensing using whispering gallium mode resonators. This time at the MPL in the division of Professor Leux convinced me that, yeah, photonics is the field in which I want to make my career in, and that also convinced me, well, to remain at the MPL, and that's a great place to do photonics research. So I decided to join the division of Professor Philip Russell in 2014 to conduct a PhD thesis on optical trapping inside hollow core photonic crystal fibers. After submitting the thesis in 2018, I remained in the group for about 1 year, and I've been working on this time the development of hollow core PCF for femtosecond laser pulse delivery for applications in multiphoton imaging. Yeah, and then in spring 2019, I decided to make a transition into industry, and I joined Menlo Systems, as mentioned previously, as an executive assistant and project leader. Besides these professional activities, so the activities I'm actually paid for, I have been involved in various professional societies. For instance, I have been a member of the action committee of EPS Young Minds, which some of you might know of. And of course, I have also been involved with Optica. In particular, I have been selected as one of the members of the 2022 Optica Ambassador class. And this is also what well, brought me here today. I'm very happy to be here today. Yeah, but of course, coming back to the topic, so this is the time or the well, the part of my career I will talk about, specifically the research I did at the MPL on using optically trapped microparticles inside PCF, inside hollow core PCS as remote sensors. Yeah, now let me well start the scientific part of this talk with a brief introduction of optical forces. And optical forces exist because light carries momentum. And whenever light is deflected by, for example, a particle, an exchange of momentum between the particle and the light is taking place. And if you now, for example, consider the situation of a dielectric sphere, which is placed inside, well, a Gaussian laser beam, then you can make, well, some simple considerations to understand the nature of these optical forces intuitively. So if you think about two rays, which are, let's say, part of this Gaussian laser beam, P1 and P2, and if you then think about from a geometrical optics perspective how these two rays are deflected by the particle, then you can see that because P1 carries more intensity than P2, the light gains a net momentum which is directed away from the center of the laser beam. Of course, due to momentum conservation, this means that the particle must, well, feel or gain a momentum which is directed towards the center of this laser beam to the region of highest intensity. And this is what gives rise to the gradient force, which pulls a particle or a dielectric to the, in most cases, to the region of highest intensity. At the same time, we see from the sketch as well that both rays, both P1 and P2, are losing momentum in the forward direction, meaning the particle must gain momentum in the forward direction. And this is what gives you the scattering force, which propels the particle in the direction of beam propagation. The typical magnitude of these forces is on the order of a few piconewton for tens of milliwatt of optical power. This, well, is somewhat not saying so much. I think the very important information is here that these optical forces are already at moderate laser powers, large enough to manipulate microscopic objects quite efficiently. Now, these optical forces can be harnessed in different experimental configurations to really, well, control and manipulate microscoped objects very precisely. And there are, well, I would say, two major configurations en route. One is a dual beam trap. The other one is the optical tweezer configuration. A dual beam trap is realized by opposing two counter-propagating weakly focused laser beams. And if you now place a particle in the vicinity of such a trap, then it will really pull towards the axis of this trap by the optical gradient forces. And at the same time, the scattering forces of the two laser beams, of course, if the power levels are balanced, will cancel each other out, such that the particle is trapped stably in the center of this trap. In contrast, an optical tweezer comprises only a single beam, which is strongly focused. Here, of course, a particle will experience a scattering force as well, but this will be compensated by a gradient force that pulls the particle to the region of high intensity, e.g. the laser focus, such that you get a stable trapping point close to the focus. Now, these traps, both configurations are fantastic, well, platforms, and they have allowed for a number of breakthroughs in many different fields, but they do have one fundamental drawback or one fundamental limitation, and that is that the laser diffraction or the field of view of the trapping objective as well limits the accessible manipulation range in a very fundamental way, right? Fortunately, there's a way to come around this issue, and that is using waveguides, in particular hollow-core waveguides, as a platform for trapping applications. In such a waveguide, light can propagate diffraction-free over distances which are only limited by the losses of the waveguide. And if you now, for example, think about a hollow-core waveguide which has somewhat of a Gaussian intensity profile, a Gaussian mode profile, then the particle which is placed inside such a hollow core will be pulled towards the center of the core by gradient force and will be propelled along the axis of the core of the fiber of the waveguide by the scattering force. There are, of course, many different types of fibers, waveguides around. We at MPL always believe that hollow-core photonic crystal fibers are a particularly interesting platform for doing this kind of experiments. Hollow-core photonic crystal fiber can be categorized in, let's say two main families. On the one hand, you have the photonic bandgap fibers. These comprise a hollow core which is surrounded by a photonic bandgap structure that provides light confinement in the core. And then on the other hand, you have the Kagome or anti-resonant type fiber structures. And here the guidance is provided by anti-resonant effect provided by the cladding that surrounds the core. And what both types of hollow core PCF have in common is that they provide a very tight light confinement inside the core with foci or core mode field diameter of, let's say, below 10 micrometer if desired, and as well as extremely low loss, which can be as small as a few dB per kilometer, actually competing with commercially available single mode fiber at this point. And this makes them really a great platform for optical trapping experiments. So it was not very surprising that when the hollow core, when the hollow core fiber was established first, it took not too long until first experiments started on optical trapping or optical manipulation inside these fibers. And this was actually done in 2002 by Benabit et al. And he and his team demonstrated that an optical particle can be levitated inside a vertically oriented hollow core photonic bandgap fiber quite efficiently. Well, and since this very first experiment on optical trapping inside hollow core PCF, a lot of work has been done, and a lot of it was actually done at the Max Planck Institute in Erlangen. For example, Schmidt et al. And Garbus et al. Demonstrated that it is possible to perform particle metrology of particles trapped inside these fibers. There has been work on demonstrating newer manipulation techniques, for instance, by the combination of optothermal effects and the optical forces. Very interesting work was, or is the work that was carried out by Sarah Unterkofler et al. She demonstrated that red blood cells, which are propelled by the scattering force inside a hollow core fiber, experience actually a shear stress that is strong enough to deform them, and this deformation can then be monitored as an increase in cell speed, and this shows that hollow core PCF are also a potential platform for doing biophysical studies. And then finally, and this is pretty much what I will be talking about in the following as well, is the flying particle sensing approach that has been first demonstrated by Bikoff et al. In 2015. So I hope this gave you some perspective on why, we believe that hollow core PCF are a great platform for doing optical trapping experiments. Let me introduce you to the outline of my talk. At first, I will introduce how it's possible to use optically trapped fluorescent microparticles for irradiation sensing. The second topic that I will cover will be using an optically trapped microlaser based on a dye-doped polymer particle as a remote temperature sensor. And then finally, and this is the part of the talk which is not related to sensing but to actually optomechanics, I will show you how a silicon nanospike can be used to achieve self-aligned and broad bit coupling to hollow core PCF. right dive into the first topic. Again, I've said it already, the very first experiments or the very first demonstration of this flying particle sensing, as we have called it at MPL, was done in 2015 by Bikov et al. So, well, the people around back at these days were the people who started these experiments. And here the underlying concept is that an optically trapped microparticle inside a hollow core PCF can be used as a microsensor to well, sense external forces or external perturbations which are present around the fiber. And in the very first experiments, they used an electrically charged microparticle to probe the presence of an electrical field along the fiber. What is happening here is that, of course, this electrically charged particle is sensitive to, well, the electric fields that are present, and it will react, as indicated here in the sketch, with displacement from the fiber core center when it, for example, passes a region where there's an electric field present, right? And this displacement can be measured by observing the fiber transmission. So that allows to use the particle, for example, to propel the particle along the fiber, along a very long fiber, if required by a given application, continuously monitoring the transmission of the fiber. And whenever there will be an electric field present, this electric field can be detected by a change in the fiber transmission. What also has been proposed in this paper in 2015 was that a radioluminescent particle could be used to, for example, detect nuclear radiation. Here the proposal was that the luminescent particle again would be propelled along the fiber axis, and whenever it would passes along a source of radiation, it will emit light, and this emitted light will then be partially captured by the fiber core modes, guided towards the fiber end phase, and that could then be detected either with a spectrometer or with a photodiode, as indicated here. And yeah, this is where I pretty much started my work on, and the results on this, so the extension of this approach to fluorescence-based radiation sensing, is what I will show you now in the following slides. This is the experimental setup that we used. The core, or well, the key piece or the heart of the setup is a hollow core photonic photonic crystal fiber, in this case a Kagome type fiber, and both ends of this fiber were clamped inside a liquid cell. On the one side, the liquid cell was connected to a syringe pump that allowed to fill the fiber with water, and the other side of this hollow core fiber was placed inside a PDMS chamber, as indicated here in this sketch. Below this PDMS chamber, there was an optical tweezer placed, and this optical tweezer now allows to trap microparticles which are in the aqueous solution in front of the fiber, and phase it, place these microparticles directly in front of the fiber core region, and then propel it inside the fiber core by the 785 nanometer titanium sapphire trapping laser that we used in this experiment. So that the particle goes, and once the particle is inside the fiber core, the speed of the particle can be very conveniently monitored using a simple Doppler velocity measurement. And of course, if you have the speed at any given time of the particle, you can then integrate the speed information to have the spatial position of the particle along the fiber. Of course, this is not everything. You might have noticed that we need an excitation source. So in this experiments, we were only aiming here for proof of principle. We used an excitation laser that was located beside the fiber to excite the fluorescent microparticle once it was when it was passing along the fiber. And of course, in transmission, we also needed detection to actually measure the fluorescence. This was emitted by the particle. Here we had both a very sensitive photodiode in operation as well as this CCD camera. In this particular work, we used fluorescent polystyrene particles, which were dye doped. The excitation wavelength was 500, well, approximately 40 nanometer, and emission was taking place at around 610 nanometers, so in the red part of the spectrum. So the very first experiment that we did here was to demonstrate that the approach is actually feasible in the first place, and for doing so, we focused our excitation laser using a cylindrical lens, such that a quite large fraction, like about 2 millimeter, or well 1700 micrometer, of the fiber was illuminated with the excitation light, and then we moved the particle along that region, and of course like I explained, the particle will show fluorescence, and this fluorescence will be captured by the fiber modes, guided towards the fiber end phase, and you can measure it, and this is what we did. And indeed, we saw here a very nice and very clear fluorescence signal with a Gaussian fit of around 720 micrometer that very nicely fitted the expected width of 1740 micrometer, as we got from the width of the focus actually. So this was great, but we were encountering strange signal here. You might notice this sharp peaks, sorry, which is separated by around 1000 micrometer here. So this is obviously a regular thing. And it was also quite systematic that these peaks in a measured fluorescence signal were also coinciding with positions of low particle speed. And now to explain this phenomena, I have to introduce you to the effect of intermodal beating. So the fundamental core of a Kagome type fiber can be described as the LB01 mode, which has a, well, let's say, it's not a Gaussian, but let's say it's a Gaussian for the matter of the discussion here. And it looks like here is plotted in this picture on the right side. Usually when you do an experiment with these types of fibers, you optimize your coupling to these kind of fundamental modes because they, well, are most nicely defined. They have the, let's say, most symmetric mode profile. And of course, there's usually also the lowest losses. However, it's almost unavoidable that at least a small fraction of higher order modes, in particular the LP11 mode, are excited as well. And both of these modes have different propagation constants. That means as they're propagating along the fiber core, they will produce a continuous interference pattern. This is what is shown in the picture here below on the right side. So what you will see is that you have a variation of intensity, a variation in field strength, so to say, both in the axial direction and in the lateral direction with this periodic oscillations that you can see here. And what is now happening if you're placing a particle inside a fiber core is that it will first of all follow a zigzag trajectory because it will also always follow the follow the regions of highest intensity. And at the same time, it will be periodically slow down and speed up because you have these regions of varying intensity, right? And you can see it here very nicely. And now what is happening is that the particle is following the zigzag trajectory every time it's passing along the core region here. So like the 0 position in the graph, you see that there's low intensity, meaning that at this positions the particle will slow down. This is what we see here as the blue curve on the left side. And yeah, these are also the positions where the particle is mostly centered in the fiber core, meaning this is the position where the particle or the fluorescence emission of the particle is most efficiently captured by the fiber core modes. And this explains this sharp peak in the measured fluorescence signal, and this also explains why these sharp peaks coincide with the positions of low particle speed. This is also confirmed by measurements that we did, experimental measurements on the period of this beating pattern here, which is 930 micrometer, and that matches the distance of the peaks quite nicely. So these measurements showed that the concept is in principle feasible. So the next thing that we were investigating is the spatial resolution of these type of sensor. For doing so, we again used our cylindrical lens, but we placed a metal tungsten wire inside the beam path, and this tungsten wire then created a very nicely defined diffraction pattern. This is and then of course we repeated the measurement. We moved the particle along the fiber and detected the fluorescence, and this is an exemplary piece of data where you can indeed very nicely see you detect the minimum in the middle, but you can also very nicely actually see the diffraction fringes here at the right and the left side of the 0 position of the particle position. And then we of course compared these fringes with what theory predicts, and there you can actually see a very nice agreement. So there is an offset in the absolute value, but the actual spatial locations of the fringes are very nicely resolved by our particle sensor. And depending on defined by the distance between the first and second order diffraction peak here, we defined the sensor spatial resolution to be on the order of 10 micrometer. And then finally, the last thing that we were interested in investigating was, of course, the linearity of the sensor. For this, we used a spherical lens, moved the particle along the focus spot of the spherical lens on the fiber, and measured the fluorescence signal strength as a function of optical excitation power. This is plotted here in this graph. And if you have a look in the inset, then you see that there's a quite nice linear behavior observed. So this was the first part of my talk. I showed you how we can use an optically trapped fluorescent white particle to perform measurements of irradiation which is present around the fiber. Building up on this experiment, we were thinking out, okay, if you can actually use a fluorescent microparticle, why not using a lasing microparticle as well for sensing application? And this brings me to the second part here, to the second topic. And I would like to start this topic with a brief introduction into a very easy and superficial introduction into whispering gallium mode microlasers. So in general, a diode microparticle, depending on the dye, of course, can form an active whispering gallium mode resonator. This is here illustrated on the left side. So if you have the dye molecule sitting, for example, at the outer or the inner surface of the microparticle, you have an incoming excitation light, then what will happen is that the dye molecule starts to emit fluorescent signals, and these fluorescent signals can then be captured inside the microparticle by means of total internal reflection. And in this case, they are propagating around the inner surface for, times to depend on the lifetime of the photons, and of course on the losses of your microcavity, so to say. And whenever this this resonance condition here on the right side is met, so whenever the optical path length around the circumference of this microparticle equals a multiple integer of the light wavelengths, an optical resonance is formed, and one can see this enhancements in the spectrum. Now, what is happening, of course, if the dye is chosen, the dye and the dye concentrations and the pump excitation power and so forth are chosen in the appropriate way, is that one can achieve lasing, right? Because we have a cavity, we have a pump, and we have an active gain medium, and this is what you need for making a laser, and this can be indeed done. Now, how is this related to sensing? Well, if you now change the temperature of this diode microparticle, you pretty much change the resonance constitution, because both the refractive index here in this equation on the right side and R, so the dimensions of the particle, are of course related to the temperature, and this change in temperature is then causing a change in the spectral location of these lasing modes, and this is exactly the effect that we employed in these experiments. This is the experimental setup that we used for doing so. It's actually very similar to the one I've previously described. The difference is that we did not use the titanium sapphire laser, but rather a 1064 laser for the trapping. And of course, since we wanted to excite the particle continuously, as it is propelled along the fiber, we additionally coupled a 532 nanometer pulsed excitation laser into the fiber core modes. For the detection and analysis of the emitted fluorescence and later the lasing, we used the spectrometer, which was placed in the setup in reflection. In this experiment, we used a larger gometype holocore PCF with a 30 micrometer core diameter, because we wanted to use large diode particles with a 15 micrometer diameter, so 5 times larger than the diameter that we used in the previous experiment, because we wanted to have as high Q factors as possible, and of course also get a lot of signal out of the experiment. And this is why we decided to go for much larger particles here. They were doped with a dye that, of course, could be excited by the 532 nanometer excitation laser, and they emitted around 600 nanometer. So here, the very first experiment that we did was to demonstrate we can actually make a diode microparticle inside a holocore PCF lasing. For doing so, we trapped a microparticle stationary inside a given position inside a holocore PCF and continuously increased the optical excitation power. This is shown here on the left side. And as you can see here, for low excitation powers, you can also already see this fluorescence spectrum appearing. But now, as we're increasing the excitation power further, we can actually see here really very nice peaks, which are separated by around 5 nanometer, which agrees very nicely with the expected free spectral range of the WISP earlier modes that we were expecting. The full width maximum of the peaks was about 3 nanometer. Of course, for proving lasing, you need to observe a threshold behavior. So we looked at the counts as a function of the pump power as well. So the spectrometer count as a function of the pump power, and there indeed we could see a very nice lasing threshold behavior, indicating a lasing threshold in this particular experimental configuration of 8 micrometer. Okay, so we knew we can make the particle lace. The very first step was taken. So the next thing that we had to do was to calibrate the temperature response of this of this lasing modes, or of the cavity modes of the diode particle. For doing so, again, we trapped a microparticle inside the fiber at a position where we have a heater placed, and then this region was heated in a very controlled way, and the emission spectra of the particle were monitored as a function of the temperature change pretty much. This is shown here in the graph on the left side. So we have here the initial spectrum at 26 degrees Celsius, and as we increase the temperature further, we see a very nice and clear blue shift. Of course, we did this not only for three temperatures, but for more temperatures to have good statistics and good data. This is plotted here on the right side, where you can see very nicely a resonance shift as a function of the temperature at a heater, and that it follows quite nicely a linear behavior with a negative slope of minus 0.122 nanometer per Kelvin, which is giving the sensor response pretty much right. From the sensor response and the standard deviation of this measurement, so to say the noise, we can deduce a minimal detectable temperature change delta T in the stationary configuration of around 2.7 Kelvin. So once we had the lasing demonstrated, once we had the temperature sensitivity calibrated, the last step that we had to take was to actually demonstrate the distributed temperature sensing. For doing so, we installed a second heater along the fiber, and then the particle was propelled along both heaters, while the emission spectra were continuously recorded and the resonance positions retrieved. So this is the result of the measurement, and you can see here from this little animation that indeed you can very nicely resolve the temperature profile here along the fiber using this diode microparticle as a temperature probe. We also made a comparison between our experimental data and numerical simulations of the temperature profile along the fiber. Here you can see that we have an offset in the absolute values, in particular at the positions of the heater actually, but we do overall very nicely reconstruct the shape of the temperature profile. So this brings me to the last topic of my talk, which is the self-aligned and broadband coupling to hollow core photonic crystal fiber based on so-called silicon nanospikes. A silicon nanospike is basically a single mode fiber tip, which is tapered down to a tip diameter on the order of a few hundreds of nanometer. This can be done by different thermal and chemical methods. And if you have a certain mastery on this, you can actually quite nicely control the geometry of this taper during the tapering process. And if this is done carefully and in an appropriate way, that one can achieve is a so-called adiabatic transition or an adiabatic evolution of this optical mode along the fiber, such that, or the nanospike, such that it always propagates in the fundamental mode, and such that the losses along the nanospike are also very small, such that you can have a high transmission along the whole device of like 90% or even more. What is happening during the tapering process is that the optical mode of the nanospike is pushed out into the surrounding environment of the waveguide. This is plotted here in this graph, where you can see the mode field diameter as a function of the nanospike radius for a nanospike immersed in water. So you pretty much see here that at some point the mode is pretty much breaking out. And this brings the question, what is happening if the nanospike is not well placed inside a bulk material like water or air, but rather inside a waveguide structure, such as a hollow core photonic crystal fiber. And what is happening indeed in this case is that the nanospike mode that spreads out from the nanospike is starting actually at some point to feel the presence of the hollow core photonic crystal fiber structure. And this provides, let's say, an additional confinement parameter, which makes the mode field diameter of this nanospike mode to converge against the mode field diameter of the hollow core photonic crystal fiber. This is here shown in this graph as the black curve and the red dashed line for a hollow core PCF with an internal core diameter of 10.7 core radius, of 10.75 micrometer. And that means that you have a transition from the nanospike mode into the hollow core photonic crystal fiber mode, and efficient coupling between the two modes can be achieved again for a core radius of 10.75 micrometer for nanospike radii that are approximately smaller than 200 nanometer. So this allows you really to have a controlled, almost single mode coupling from the nanospike into the hollow core PCF mode, without relying, for example, on free space optics like lenses. But this is not the full story yet. So this is the coupling. The other effect that is taking place in this setting is an optomechanical self-trapping effect. So what's happening here actually is that the hollow core fiber and the nanospike form what you could call it a super mode. So a mode which is defined by both the nanospike and the hollow core PCF structure. And well, any movement now in of this nanospike tip inside the fiber core will give rise to an optomechanical force, an optical force due to an optomechanical potential U which is present, and this optical force can be calculated by the equation given here on the right side. So this force depends on the insertion length of the nanospike inside the fiber core and the optical power, and then of course, and this is important to know, on the change of the effective index of this super mode, so to say, as a function of the displacement of the nanospike from the core center. So this is the last term in this equation here on the right side. So what does it mean? It pretty much does mean that when the nanospike is placed inside the fiber core and a sufficiently high power is launched into the system, then there will be a significant optical force be present that will pull the tip of the nanospike back towards the core center. Using this equation, which is very nicely derived in this paper from Rodriguez here, Optic Letters 2017, and also picked up in the publications of my colleagues Xi et al. In Optica in 2016, it's quite easily possible to calculate the stiffness, or the optical force, and so the stiffness of this optomechanical forces. This is done here for a scenario in which an insertion length of this nanospike of 100 micrometer into the core is assumed. And you see here that for this we achieve what the value is presented here. I don't want to go into details, but what is important to know and to understand here is that these optical forces, as you can see here by the indicated line, which gives the mechanical stiffness of the nanospike, these optical forces of the optical stiffness is actually significantly larger than the mechanical stiffness, and that effectively means that the optical forces are large enough to actually bend the nanospike inside the fiber core. And this then gives rise to an optomechanical trapping and an optomechanical self-stabilization effect. And we have seen in the previous slide that the nanospike also facilitates efficient, and as we will see later, also broadband coupling to the hollow core PCF. So of course, this was somewhat the basic idea, the basic theory behind this experiment. But of course, we wanted to demonstrate this in experiment. This is the setup that we used for doing so. We again relied on a 1064 nanometer trapping laser, which was coupled into a single mode fiber. We had here in the beginning some diagnostics. This trapping laser was then combined with a supercontinuum source using a wavelength division multiplexer, and this combined trapping light and supercontinuum light was then fed into a nanospike, and the nanospike was interfaced inside a microfluidic chip with a hollow core photonic crystal fiber. Both the nanospike and the fiber were placed on positioning stages, of course, to align them with respect to each other and to eventually insert the spike into the PCF as shown here in the inset. And then, of course, in the transmission side of the fiber, we had various diagnostics available to, well, do whatever analysis we think was necessary for making a certain claim or a certain statement. In this experiment, we can use the Kagome type fiber and with a core diameter of, I think, around 22 micrometer. Here we achieve coupling efficiency of around 50% at 1064 nanometer, as well as, this is also interesting to know, a very extremely low back reflection, which is due to the adiabatic evolution of the nanospike mode along the nanospike axis. So the first thing that we wanted to show here was the optomechanical self-aligning effect. For this, let's assume a scenario in which a nanospike has an initial offset capital delta at its base with respect to the fiber core center, and here in the fiber core, actually, we have an offset of small delta. And what is acting, or the forces that are acting on the nanospike in this setting are pretty much the optical force, which is, as we have learned, a force that acts towards the core center, meaning that it pulls the tip of the nanospike towards the core center, and there is a counteracting mechanical force, which in this setting acts in the opposite direction. And of course, here, the tip offset, small delta, is then given by the force equilibrium between these two forces. This tip offset, small delta, can be quite easily calculated. Here on the left side, you see pretty much the evolution of delta as a function of launched optical power for three different initial offsets, capital delta, and there you can see that pretty much for all offsets, the final tip position for increasing optical power is converging to be the core center, so the zero position, so to say. Of course, it's very difficult to measure such a setting with high spatial resolution, the position of such a fragile element as the nanospike is. So what we did here is to rely on not measuring the spatial position when investigating these effects, but rather measuring the transmission, because the transmission from the nanospike into the PCF is depending on the fiber tip position and the nanospike tip position, sorry. This is shown in this graph here, where we measured the transmission in arbitrary units as a function of the nanospike displacement from a fiber core center. And then you can actually see that when you move away, like, I don't know, 2 or 3 micrometer from the core center, then you can see actually a significant drop of around, well, 20% in transmission. And of course, this is an effect that can be measured. And so what we did to demonstrating these effects is to measure the so-called relative transmission. So the ratio of the transmitted power over the ratio of the launch power. And of course, you would expect that for increasing optical power, this value increases because the nanospike is more nicely aligned to the core center. And this is indeed what we have observed in the experiment. So this graph shows the relative transmission as a function of optical power and really shows that there is a significant increase with increasing power levels, demonstrating the optomechanical self-aligning effect. So this was all done under steady state settings. So we just always increased the optical power, measured the transmission, and we did not look at the dynamics. But of course, this is something that is also interesting. So we did experiments for the investigation of this temporal dynamics of the nanospike position. The nanospike, or these temporal dynamics, are described by this equation of motion here on the right side, where you have a drag force, a term for the drag force, a term for the mechanical force, as well as a term for the optical forces. And the solution of this equation is an exponential equation, which has a term tau in it, a decay constant, which is given as the ratio of the drag gamma over the sum of the optical and the mechanical stiffnesses. We investigated the temporal dynamics experimentally by continuously shutting the laser, the trapping laser on and off. This is what you can see here on the left side, and these absolute values already show you that there is, well, obviously, something going on. There is a temporal dynamic. This becomes even more clearer when you look at the normalized transmission, the normalized relative transmission, and if you then actually look into, make a zoom in into one of these trials, then you can actually indeed see that the normalized relative transmission can be very nicely defined or described by an exponential fit, as shown here, with a time constant tau of the order of, well, in this case, 2.75 seconds. The equation in the upper part of the slide says that tau has a dependence on the optical forces. That makes sense. That also means that in an experiment you should be able to observe a power dependency of tau. So what we did is to measure the time constant for different optical powers. This is plotted here on the right side, where you can see an increase that you would expect in the time constant with increasing optical power, and also a quite decent agreement, I would say, with a simple model that we developed for calculating the time constant. So this brings me to the last topic of this part of the talk, which is the broadband coupling. So here the idea was that, okay, we can now use this technique to do the self-alignment to stably launch this trapping laser light, but can we do more? For doing so, we additionally launched the supercontinuum source into the nanospike and did a measurement series where we started with a displaced tip, so a displaced nanospike tip inside the fiber core and low optical trapping powers. And here you can clearly see that you have a lot of light in the higher orbital modes. And as we now increased the trapping power step by step, we are seeing that the mode profile is actually converging very nicely towards that of the fundamental core mode, indicating that indeed the trapping laser pulls the nanospike towards the core center, and that allows more efficient coupling of the supercontinuum into the fundamental core mode. We also investigated whether we can use this trapping laser as a stabilization element, so to say, against perturbation. So for this, we placed the nanospike manually via the positioning stages inside the core center and launched, either low or high trapping power, and continuously, or then monitored the change in the mode profile of the supercontinuum when we changed the position of the tip. So this is shown here, where you can see the left side, the results pretty much for low optical trapping power for 30 milliwatt, and there should be actually no significant optical forces be present. You can see here that overall the mode profiles, if you move the nanospike tip manually inside the fiber core, gets actually distorted quite a lot. Here on the right side, on the other hand, you have the mode profiles at a trapping power of 380 milliwatts. And here you can see, while there is some distortion, overall the mode profile remains more stable, indicating that indeed the trapping laser, which the trapping laser is keeping the nanospike safely inside or at the core center, and is therefore providing a certain stabilization, a certain protection against, for example, mechanical perturbations. Finally, this is the last experiment that we did here, was the demonstration of the broadband interference coupling. There we pretty much made a comparison between the light that we launched into the fiber and the light which is coming through the fiber. So air as a function of lambda, and the reference is a function of lambda, and the transmission as a function of lambda. And from this is given here on the left axis in dBm. And of course, from this you can very easily calculate the coupling efficiency, and this is plotted here as the red curve. And here we can see that we can actually get over 500 nanometer bandwidth coupling efficiencies of more than 30%, which is quite a significant thing, because usually it's not so super easy to get coupling efficiencies over such a large bandwidth with let's say traditional free space optics, for example. So that brings me to the summary. I have talked about 3 topics. The first topic was the irradiation sensing using optically trapped fluorescent particles. Here I have shown you data that back up the claim that we can achieve a spatial resolution on the order of 10 micrometer with this approach. Here I'm also claiming that this type of sensor provides an unprecedented spectral flexibility. we did measurements there, so I have the data, but I will not show it for time reasons. But this is also simply because you can pretty much change the particle they're using, right? You can use, like in our case, a particle which is fluorescent, or which is emitting fluorescence upon excitation is 500 nanometers. But for example, if you're interested in detecting, for example, UV light, you simply take a microparticle which is sensitive towards UV light, and then you pretty much can change the spectral sensitivity of the sensor with minimal ease, of course, given that you have a particle with a student dopant available. In the second part of the talk, I showed you a temperature sensing using an optical trap microlaser. Here I showed you both a temperature resolution of 2.7 Kelvin in a stationary sensing configuration, as well as a millimeter spatial resolution in distributed sensing scenarios. And then finally, I've showed you the self-aligned and proper coupling to hollow core PCF using a silicon nanospike. And here we can use a trapping laser to firstly align and self-stabilize the nanospike inside the fiber core center, and then further use this nanospike to launch also broadband signals into this into the hollow core PCF core. And here we have achieved coupling efficiencies of 30% or even more over a 500 nanometer bandwidth. So that's well, this is the end of the scientific talk. I took the freedom, because I'm here as one of the optical ambassadors of the 2022 class, to make some advertisement, some promotion for the currently ongoing call for the optical ambassador class 2023. I don't want to go into too much detail here. I just want to emphasize that being an optical ambassador is a great opportunity, not only for the own professional and personal development, but also for well, giving something back to the photonics community. So if you already have demonstrated some leadership in your, let's say, local photonics communities, maybe in your local student chapter, and if you're interested in bringing this to a higher level, then please consider to submit an application. The deadline is due, or the deadline is on November 15, so there is still time. If you have any questions on the application process, on how to draft an application, then please feel free to reach out to me anytime. And well, with this, I would like to thank you very much for your attention. I'm happy to take any questions, and well, may the light be with you.
Yeah, thank you very much for this great presentation. If anyone has any questions, you may ask. Okay, I believe we don't have any questions for you. I would like to thank you again for this great presentation.
Thank you very much. Have a great day, and thanks again for the invitation.
Thank you very much. Hope to see you again.
Bye. Take care.
And now he's serving as IEEE Photonics and SSCS Turkey Chapter Chair. And prior to his faculty position, he worked as postdoctoral researcher in Photonics Lab in George Washington University. Yes, in his talk, he is going to mention, and he's going to start with the tuning mechanism in photonic devices via MEMS, as we call, and later we will discuss different types of photonic devices and how they were implemented, not only to build switchers and phase shifters, but also convert photonic devices into tunable couplers and grating couplers. Now I would like to present you to Dr. Hasan Göktaş.
Today I'm going to present photonic MEMS for programmable photonic integrated circuit. I know we already did photonic integrated circuit last night and today morning. Okay. The first time I started to build the circuit in 2008 back in the USA with this microelectronic chip in here. That's my first baby. Later, of course, I continued my work with the MEMS and then photonics, and today's presentation is about combining all these three together. The outline is as follows. We're going to start with the tuning for photonic integrated circuit, which we call in the abbreviation as PIC. Then we're going to continue with the comparison of different techniques. We briefly already saw it, but I'm going to show more examples in this. And then I'm going to talk about this photonic chip that we built this year with the results. So why we need tuning, we already saw in Professor Wim Bogaerts' presentation and the Professor Sudip's presentation. But let's briefly go over it. One of the widely used photonic device is the wavelength division multiplexing. It basically takes different laser sources, combine them together, which is a mux, and then or getting a laser source, and then separating into the different frequencies, that is the demux. So why we need tuning? If we look at how the photonic circuit looks like for the WDM, we can see ring resonators in different locations. So basically, if you convert this ring resonator to tunable ring resonator, then we can change this WDM into different frequencies, which will prevent us to build the chips again and again and saves us too much money and the time, because it's going to take a few minutes rather than 6 months for building, plus so much money. Another example is using mesh. We already saw in Professor Wim Bogaerts' presentation. In the mesh structure, we can build any circuit we want, and the typical fundamental devices or the method that we use is either using a coupler and a phase shifter, and we're going to build either cross state, bar state, and using tunable coupler to direct or manipulate the light to build any circuit that we want. And we can see here the Mach-Zehnder interferometer with the phase shifter. That's one of the implementation to build this crossbar and the bar state. And we can see another paper here. This is a red and honeycomb is a rectangle mesh structure. We can see we can build the two resonators next to each other or Mach-Zehnder above by simply tuning these devices and playing with them like as a coupler and shifter. This is another implementation. We know all the electronic circuits is actually going towards the photonic integrated circuit, and this is one of them. 4-bit digital to analog converter in photonic implementation, and by doing that we need modulators, electro-optic modulators, and of course in here if we make them tunable, again we make this DAC tunable, and we can modify it in any way that we want. Another example is the photonic dot product engine. That is basically matrix multiplication, as we know, and most widely used in neural networks, AI, and deep learning. So you can see wavelength division multiplexing here, the laser source comes in here, and you have a switch in here. So if the switches are on, then the light comes in here, resonates in here, and then continue to resonate, and then go towards the output, and you get the max multiplication in the output, which is lambda 1 times the B0. Here, lambda 1 is the A0, so it's A0 times B0. If you continue like this, you will get A0, B0 plus A1, B1 plus something like that. So here we can see not only tunable devices, but also the switch we need for the photonic integrated circuit, because here they applied a switch in here. So these are the switches. So if B1 is 1, the switch is closed. If B1 is 0, the switch is on. As in this way, you can get the multiplication with these two matrices. Okay, so after those examples, let's compare different techniques for this tuning and switch operation. So thermo-optic is the most popular because it's the easiest to implement. And then optomechanic is another way. But recently, MEMS gets too much attention because it's a zero power consumption. Plus, thermo-optic, because you are applying heat on the surface, if you have, let's say, thousands or millions of devices on the surface, it's going to heat up. And that is one of the bottlenecks in the CMOS circuit nowadays. So that's why MEMS is very popular. Not only because it doesn't consume any power at all, but also it doesn't have any heating problem. Let's talk first about tuning via Joule heating and look at some examples. We can see here ring resonators combined together. When you apply heat, it changes the refractive index of the silicon. By changing the refractive index of the silicon, you are actually changing the effective index of the system. So you are shifting the frequency. So that will give us a phase shift. Okay, that's one way to apply, which is the easiest way. You can see these are the heaters. Hold on. Okay, so these are the heaters you can see here. For each ring, you have one heater. Another example by using the heater is a tuning micro ring resonators. So we can see 5 of them together in here, and we have a heater in here. By heating the structure, you can see the frequency shifts to the left or depending on the operation. Here we can see if we have 3 ring resonators, that's for 3 ring resonators. If we have 4, if we have 5, so increasing the ring resonator, numbers of ring resonator, you can see the quad factor is increasing because of the coupling effect. But overall, back to the point, by using heater, simply you can just change the refractive index and you can just shift the frequency, or you can change the phase. That's what we can also say it in this way. This is Mach Zehnder. Also, there's a heater in this here, Mach Zehnder. By heating the Mach Zehnder, you can see the frequencies change. However, as we talk, if you have thousands or millions of the Mach Zehnder on the surface, it's going to accumulate the heat and probably burn out the chip. One solution is etch the heater underneath the heater so you can prevent the overheating on the surface. Well, let's talk about the tuning via electrostatic actuation, which we call it MEMS. So we can see one example in here. This is a Mach Zehnder, and there's a resonator in here. Actually, it's just a fixed beam. When you apply voltage, just bending down, and we take out the voltage, just get back to the normal state. So when it bends, when the displacement changes, the mode gets affected, and of course the effective index changing. By changing the effective index, you can get the frequency shift. That's very easy, no power consumption because there is no current flowing between two electrostatic conductors. This is another example. You can see the Mach Zehnder, and you can see this MEMS structure in here. When you apply the pulling voltage, that structure bends down and it changes the refractive index on this side. So in this way, you can change the phase in each branch separately in any way that you want. So you can get a different response in the output depending on the power and the phase. And we can see in here how the refractive index changing by changing the gap. And you can also see the mode is also changing. So it's in both sides, but in here mostly in the downside. So this is another example for the ring resonator. So this structure is actually released on the edges, so it can move down and up. And there's another electrostatic conductor underneath, so you are applying electrostatic force. It's just bend down or bend up. By doing that, you are changing the coupling ratio and also changing the phase. You can see how the phase changes for this ring resonator. Well, this is another example. You can see the coupling length in here. By changing coupling length, by simply having this MEMS structure in here, this comp structure, when you apply voltage, this guy moves back or front depending on the applying voltage in here. That's why when you change the coupler length, you can simply change the FSR, which you can change simply the phase. This is actually one of the best I like because it's the combination of both the switch and the phase change in here. So this guy, if you apply the specific voltage in the comp structure, it will bend down. So the laser comes in here and resonates in here and going drop or add port, right? However, if you don't apply the voltage, this guy have a large space in here, so there is no coupling in here. The laser comes in here and goes towards. So this comp structure in here works as a switch, and this guy in here works as a tuning because if you apply voltage in here, then you are playing with the coupling length in here. That will play the resonance frequency. So we can see here how the resonance frequency change with respect to the voltage applied to this tuning actuator. Okay, let's talk about the building tunable coupler. Actually, we already have it in here. This is another example. So here we have a tunable coupler. Applying voltage, this guy bends towards each other and gets close to each other, so you will get a high voltage. But if you apply voltage in here, then the separation increases and the voltage decreases. So it's basically the coupling decreases. So this is the tunable coupler. You can play with the power ratio in the output. Okay, another example is a switch. So here by itself is just on and off, right? And it's very popular for the data centers because zero power consumption, very fast, and very good for very compatible with the photonic integrated circuits. What happens is here, if the gap is high, there is no coupling. If the gap is small, then there's a coupling, right? And the structure in here, you can see the light comes in here. If there is no coupling, the light goes towards the other section, the other box. If there's a coupling, of course, it just couples to here and goes in this direction, and then couples to this guy, and then goes in this direction. So you can route the signal in any way you want with this mesh structure, and the mesh, each box has a separate NAND switch inside. So how it works? Basically, you have the spring guys in the spring in here, which is the comp structure. When you apply the voltage, you can see this side and this side, which we can see it in SEM view in here. It just opens or close. We can also see if it is open. So if it is open, yes, the green one, we can see there is a very small transmission here, so much loss in here. If it is closed, there's a nice 0 dB in the transmission. So the open position minus 50 dB is almost nothing, so it's a very high loss, so it's open. And this guy is when it's closed, it's pretty much transmit all the signal. This is another switch example. So when we apply the voltage in the comp structure, it just moves up and down. When it moves up, these guys gets to each other, and you can get the output. So we can see here when it gets in the same level, in horizontally, we can get the output. When it is open, we get no output. That's another simple electrostatic actuation switch. This is another switch. We can see it in here. This view, it's very simple. But this guy looks complex because the zoom out view. You can see if there's a hole, the signal just reflects back. But if there is no hole, the signal just passes through the other side. So there's a comp in here. By moving forward and backward, you can decide if there's a hole or not. While by doing that, you can decide if there's a signal transmitted or there is no signal transmission, right? And we can see the mode shape in here, no signal transmission and signal transmission. Another simple example. Well, another example is the coupler, grating coupler. We know when there's one of the popular way that you send the light to the surface is you shine the laser on the spot, and you have a grating structure here that gets most of the signal and direct towards the waveguide. And of course, the rest goes towards the silicon substrate, which is basically absorbed throughout the substrate. And sure, it is easy if it is good. It is good if you can move this grating coupler so that you can get best alignment with the light source, right? To do that, you can just etch underneath the grating coupler, make it electrostatic resonator, okay, just a cantilever. Applying voltage, you can just change the shape. By changing the shape, you can change the angle. So when the light comes, you can catch the best angle, and so that you can catch the most of the light, so you can direct towards the waveguide. And we can see it in here. By changing the angle, you can get the most, and you can see the tuning. You can get better signal comparison to the without any deformation or bending. This is another example for the grating coupler. Again, you are playing with the angle of the surface, and you are just increasing the power ratio that the coupler is getting, right? So it's bending down, it's just changing the angle, so more light coming towards the waveguide. Okay, so this is our photonic chip. It's our end. We just received maybe 2 weeks ago, I guess. Of course, we did it in the USA. We fabricated in the USA, we tested in the USA. And I'm gonna show some pictures, not everything, because there are some things that we haven't published yet. And without going towards this, and this is the map structures in here too. So the goal is basically combining these 3 guys together to get the reprogrammable photonic integrated circuit. Okay. I'm not showing everything, just to zoom in for a specific section, but still we can see some ring resonators, Mach-Zehnder and Michelson interferometer on the surface. And we did the SEM in the TAM in this building, maybe 10 days ago. Okay, this is Mach-Zehnder T and TM mode, different modes. We did different width, different dimensions, whatever. And on the right side, we can see the measurement, how the measurement match with the simulation and the modeling. And we can see pretty much they are well matched. You can see the percentage error between the measurement and the simulation and modeling. It's mostly between 0.7 and 4.88. The worst case is 4.88% difference between the simulation and the measurement. That's how close the results are. And this is Michelson interferometer. And also we did ring resonators, of course. We can see the measurement versus the simulation, the measurement up and the simulation down, are pretty much close to each other again. And of course, changing the ring dimension, we get, of course, different resonance shape. This is another ring resonator. I'm not telling which one is which one, but just to showing a bulk idea about what we are doing. Okay, I guess that's all for my presentation. If you have any question, I'm glad, I will be happy to get it.
How about the laser?
Okay.
The second one is what is the fabrication method? What first one is fabrication method? Which method?
Oh, fabrication method. Okay.
The second one is the web laser source.
Okay, fabrication method for this PIC.
Yes.
We use CPEC to library in. It's a collaboration between the Canada and the USA. And it's actually SY wafer, silicon, oxide silicon. And the silicon is like 220 nanometer thick. And oxide is maybe 0.5 micron. So we use their library, we use their process to fabricate it. What was the second question? Okay. Back in 2015, when I was doing postdoc, which I continued to work in Turkey when I came back for the mandatory test, we actually did a quantum tunnel junction on-chip laser source. We published in ACS Photonics and we applied for the patent, which is right now in US national patent phase. By the way, we got another patent acceptance registered today. That's what I got recently by email while coming towards here. You can do both on-chip and off-chip. The on-chip, you have to make sure that the laser source is reliable. One of the challenge for the on-chip laser source is the reliability. But mostly when you're building a prototype, especially the photonic integrated circuit, you would like to test with off-chip laser source. If everything works well, then you can plug the on-chip source and make everything on-chip. Even the presentation last night and today morning, you will see, you saw it, some companies did photonic integrated circuit combined with the microelectronic. And probably you noticed that there's a laser source on the PCB connected to the chip. So that's how people approach, because on-chip laser sources are still not good for the market, still in improving itself. Okay, so what they do, you are just sending one laser source to the chip. Of course, each device, each photonic device has a loss, right? So when you have the juice in the beginning, it's just decreasing and decreasing. So fan in and fan out. What happens is just decrease and decrease. At some point, you don't have enough power to drive the circuit. That's one problem. That's why people want to do the on-chip without worrying about this fan out and fan in problem. But right now, mostly it's off-chip. Yeah. No question? Well, be delighted with you. Thank you. It's all yours, Professor. Thank you so much.
Thank you, Hasan. I hope everybody can hear me well, and I hope that you can see your the slides in presenter mode. Is that all okay?
It looks perfect.
Thank you so much. I appreciate you, all of you, making it to the talk, albeit me being remote. I would have preferred to be there in person, but such are the circumstances. I'm sure next time. So what I would like to talk to you about today is a platform that is bound to complement existing silicon photonics, but it is a slightly different platform that includes slightly unconventional materials for optics, which are metals. But I would like to show you how this platform could be easily used to outperform silicon photonics in its best strength, which is data communications. Before I move on, I want to acknowledge the individuals who have been contributing to the work I'll present to you, Pohan, Ewan, Charles, and Wen, but I would like to also acknowledge the students who are working now on the next generations, Nasser, Eric, and Francis. So the talk outline will look something like that. I would like to speak about CMOS scaling laws and where is silicon photonics contributing to the enhancement of CMOS scalability. I would like to then start to look at, based on these existing optical solutions offered by silicon, I would like to discuss with you some of the limitations that are bound by the ability of silicon to shrink and to be able to provide performance with low energy and no thermal control. Then I would like to discuss with you this platform, and it's based on plasmonics that we've been developing, and show you some results for a transmitter and receiver function that is fully CMOS compatible, could be built on the front or the back end of line. And with the results of these transceiver, I'd like to compare them with existing results from other systems, such as silicon photonic implementations of transmitter receiver function for data comms. And then this platform is not just a one-trick pony. It just offers an incredible amount of potential for communications, but for data comms and CMOS, but I will also touch upon in the last few slides, if there is time, on its potential to contribute also to optical communications and quantum computing. So the electronic industry itself has had a bit of a setback during the pandemic for obvious reasons, but its annual growth rate, the cumulative one, has been sometimes up to 6% and 10% sometimes around 2010, and it continues to be projected to have a growth rate of 4 or 5% a year. Why, given the size of CMOS and electronics, be it well above $2 trillion industry, how and why could it be growing at such a high rate? Well, sort of a consulting company called Prismark sees that smartphones have contributed to some of the early rise in the 2014 and 17, etc. But now the cycle is driven by data centers, cloud automation, sensors, 5G, AI. That is driving the requirement for us to have CMOS that is more scalable and much more capable than what we have right now, despite of the astounding successes that we've had all along. So there is still room for improvement. For those of us who do not come from the electronics background, it is interesting to note that right now, the fashion by which the CMOS industry is growing is not by pursuing only Moore's law. Moore's law is saturating. The fashion by which it's growing, it is actually building a system in a package, integrating it based on heterogeneous integration to enable functions that are not possible using a few chiplets on their own. There are lots of examples offered by Intel, NVIDIA, Xilinx, and AMD, for example. Some of these have merged since, but the idea is the following. If you would like to have a system that has lots and lots of capability, you would eventually need I/O, memory, CPU, GPU, and the like, DRAM, SRAM, etc. However, all these happen with technologies and flavors and functions that are different from one another. So the best way for you to integrate them together is not to make one chip monolithic, because the chip itself has got a maximum size, but the way to do this is heterogeneous integration. To put all these chiplets on some sort of an interposer, to add them together. The examples are given in the middle of the slide, and by doing so, you can eventually get the functions to scale up without having to scale the CMOS node itself, going from 10 to 7 to 4 nanometers and below. This is attractive, but some of the major bottlenecks in this approach is that every single chiplet has to talk to one another. So it turns out the performance of those chiplets together is not dictated by the individual function of each one. The performance, it turns out, is actually limited and dictated by the interconnection speed between each one of those. Right now, the SerDes that would be useful in certain situations is sort of plateauing at 112 gigabit per second. Can we do better? Because inside of the chiplet itself, the speeds of information processing are significantly higher than that. So that serves as a main bottleneck. If you take a look at all the metrics, you'll find that the total chip bandwidth ferrying data in and out of the, if you like, of the chip itself is increasing rapidly. And there is no way for us to be able to meet the demand in the future, given the current technologies. Why is that? Because the transmission loss, as shown on the top right-hand side, increases with frequency. So as you increase the bandwidth of these, the losses will increase. You'll need more power to drive this interconnection. This is just the power to move data. It's not even power to do computation or anything else for that matter. Perhaps the best example to typify that is the graph on the lower right, which shows the total power in the package and the portion thereof that is the off-chip interconnection. As you can see, around now, most of the power is the power needed on a chip is needed to move data out of the chip to the outside world. So moving information has always been an issue. Optical communications, which is a much longer distance than what we're talking about on a chiplet, has solved that using optics. That's because the energy needed to communicate is extremely dependent on where you're communicating and the distance that you're communicating. So onboard communication can, for example, provide reasonable distance until a certain length, after which the energy per bit goes up exponentially. The same for the in-package, the same for the on-chip. This is the same story. It's just that the powers involved are different. They depend on the distance, and the speeds involved are different. They depend also on the distance and the power. So there is definitely room for improvement on what silicon photonics is offering right now on the datacom side on CMOS. Is that affecting CMOS? It absolutely is. If you look at the bandwidth of the CMOS chiplets themselves versus other metrics in CMOS, such as, for example, the logic density and the memory density, you will find that the logic density and the memory density have been growing exponentially since the 70s, following Moore's law. The logic density is still growing up till now, but it's starting to saturate. The memory density is growing, albeit with a slightly more modest slope. But look at the interconnect density on the plot on the right-hand side. The interconnect density has been absolute failure because it's been growing with an extremely poor slope since the 2000s. There are lots and lots of work trying to mitigate and improve upon that. But as you can see, it's not looking promising given the existing technologies. Once optics came in, it improved upon things by at least a factor of 10, but it's still somewhat saturated. A very good metric also for us to understand is the comparison between how electronics has conventionally been able to move data around CMOS versus optics. Optics exists on the right-hand side and the electronics on the left-hand side. This is a plot that shows you a figure of merit of how to communicate in CMOS versus the distance that you need to communicate in. And as you can imagine, the efficiency that electronics provides is very high, orders of magnitude higher than optics. But it only works for, on the left-hand side, for significantly shorter distances. Optics, on the other hand, can go longer distances, as shown on the bottom right, but it has significantly lower efficiency. But if we are going to build systems in a package and heterogeneous integration, as I shared with you before, we need the efficiency to be high, but we also need the distances to be higher than what exists on a chiplet. So we need to fill and populate the top right-hand triangle there. Is silicon doing that job? We'll see. Is there something that can do that job? Absolutely. So what I would like to discuss with you right now, how is silicon photonics itself contributing to improving upon that efficiency versus length, and where is it succeeding and where is it limited? Silicon photonics provides incredible advantages over SerDes at a given set of parameters. It's lower attenuation, believe it or not, than the electronics. You can multiplex in the frequency domain, wavelength division multiplexing, and you can build all this in CMOS compatible die. However, existing silicon photonics are limited by diffraction. If you look at the cartoon up on the top right, you'll find that as you try to shrink these features that guide light, you will find that to reduce the footprint and increase the density, you will find that the light escapes the structures. If you look at some of the lowest energy per bit devices that have been developed and are being used in CMOS, you'll find they're based on rings, like shown on the lower right-hand side, and or Mach-Zehnder modulators. The rings themselves are extremely sensitive to thermal effects. A CMOS chip, if it doesn't have optics, it could work over 100 degrees. If it has optics, beyond a few degrees, it cannot operate and it needs actuation. There are slightly better devices, such as Mach-Zehnder modulators on the bottom center, but these devices are significantly larger than their resonant and hence temperature sensitive counterparts. So there's lots to be desired from photonics right now. It has amazing advantages. It provided a leap in what can be done instead of SerDes, but it still has some serious limitations. This is one of the most notable examples that was developed based on Berkeley and MIT work. It then was used as the basis of a company called IR Labs, where there are photonic interconnection circuits on the exact same CMOS as two reduced instruction set processors, as well as the memory that connects them. And in this case, the photonics are used to connect the light between the memory and the RISC processors. What I would like to share with you here is that although this was a feat and it's fueling incredible amount of work, look at the disparity. There are two RISC processors. There is about a couple of megs of memory, and look at the amount of circuits needed to control the optics. It requires an incredible amount of space, a lot of real estate, and that is cost. Go further than that and look at two optical devices. Two optical devices are the size of half a megabyte of RAM. There's a huge incompatibility or disparity between the sizes of the optics and the sizes of the electronics. So when you end up putting them on the same CMOS chip, you're using an incredibly valuable real estate to put only a handful or a modest number of photonic components as opposed to electronics. Furthermore, for you to be able to use these optical devices well, you need to make them very resonant so they're low loss. Sorry, so they're actually low energy consumption. That means that these devices will end up being extremely temperature sensitive and sometimes also lower bandwidth than what we would like. And this is typified by some of the numbers for that particular example. It's a slightly dated example, but it's still representative. However, this company and the work by both labs, Berkeley and MIT, carried out incredible sort of results, if you will. They were able to make gigabit per second links between electronics and photonics. They were able to have bandwidth densities larger than 1 terabit per second per millimeter. This is definitely on the order of what SerDes, the electrical counterpart, can do at this point in time. All that was carried out using devices that were built on CMOS, and it's completely compatible with integration in the multi-chip interposer picture that I shared with you at the beginning in the introduction. So these results are extremely promising. A terabit, 10 or 5 terabits per second per millimeter is extremely promising. However, for us to be able to utilize the potential of CMOS and scale it to address the increasing demand of artificial intelligence, machine learning chips, as well as 5G chips, etc., this interconnection density needs to be much, much larger than a few terabits per second. The problem of doing that is that the optical devices are energy hungry and big. So the density limitation cannot be very large. So let me explain to you the platform that we have been developing for a decade or so. This platform is based on plasmonics. I am going to assume that not many of us understand what plasmonics are, so I'll just take a moment to explain what that is and the distinctions of that in comparison to silicon photonics. When it comes to silicon photonics, most of the devices are implemented with crystalline silicon. And this silicon guides and contains and confines light based on interference, and hence diffraction limits that process. So as you make these features smaller in order to make this density higher, you are no longer able to localize the light. However, if you use metals, you can, as shown on the right-hand side at the bottom, you can guide light at interfaces between materials that have positive and negative permittivity. And these guided modes are very resilient to reduction in size, and they remain guided at much smaller dimensions. Note that the left and the right-hand side are about a factor of 10 different than one another in scale. However, this is not all sort of fun and games. The main disadvantage, the community have known about this for 50, 60 years. The main disadvantage is that metals annihilate light at much expedited rates than dielectrics, which don't at all. So if you make a device on the right-hand side, it will be significantly lossier. Let's examine that in a minute. Given these attributes, there were some individuals, most notably in IZTECH or groups, which have built extremely sophisticated, extremely promising devices on the tens of micron size that utilize plasmonics. Because these devices were small, they had very large bandwidths on the order of 100 gigabit per second, but they were also very lossy. So they were much more or much less efficient overall than their silicon counterparts, but they were smaller. So can we do something in between? Can we actually bridge that gap and mitigate some of these drawbacks while utilizing and benefiting from the advantages? So we came up with a structure that not only uses metals, but it also uses metals in a configuration where there are more than one waveguide in the same structure. And that offers us the opportunity to obtain a few more degrees of freedom that we can utilize to optimize the structure and minimize the losses. A typical structure looks like so. It's based on dielectrics, such as silicon and amorphous silicon and low index dielectrics and metals. But this structure, if you look at it, if you tune its dimensions, you end up exciting supermodes in that particular structure. The cross section of these supermodes are shown on the left-hand side with the red plots. And these modes are localized, and their losses, if you look at the right-hand side, could be minimized by a couple of orders of magnitude when in comparison to its pure, simple plasmonic counterparts. That's very. Why? Because if not only that you're reducing losses, there are lots of individuals and groups that do great work reducing the losses, but they either use CMOS incompatible materials or they make the mode so very large that really defeats the purpose of reducing the losses anyways in the first place. Increasing the density in the first place or reducing the dimensions. In this case, if you look at the blue point on the plots on the right-hand side, we not only reduce the losses, but we maintain the confinement or the mode area within extremely small numbers. This was published in Science Advances a couple of years ago. So what we'd like to do is to take this concept, which we developed a few years back, and actually place it in transceivers that could be situated on a CMOS chip on the front end of line or the back end of line where you don't have crystalline materials, and see how it fares. What are the elements of a transceiver? Well, the elements of a transceiver are a transmitter, modulator in this case, the light source, which we will use exactly like what silicon photonics does, and a detector, the receiver side, and preferably, if we can, to have a filter. So we built a ring resonator-based filter in the same structure. Let me share the results with you. If you look at the filter itself, it's based on a ring resonator. It has metals in it, yet it has an extinction ratio of 30 decibels. 30 decibels is a number that is not really tenable in silicon nitride, or anywhere at all. Something slightly more intriguing is that if you look at the effective wavelength selectivity of it, or the Purcell factor, effective Purcell factor, you will find that the Purcell factor is depicted on the top right plot with the red star. This red star is not only higher effective Purcell factor than silicon nitride, which is extremely low loss, but it's also higher Purcell factor than even silicon, which is the king of cavities as such. Naturally, it's also higher by a few orders of magnitude than previous plasmonic counterparts. So that's quite exciting because that tells you that you can have devices, as we've anticipated from our theory, that have such low loss that they can compete with the lowest loss structures in the world. In fact, the only effective Purcell factor that is larger than these metallic structures is photonic bandgap cavities, which are not only relatively low loss because they're made out of low loss dielectrics and fully guided, but they're also extremely complex to make with very low yield, as you need to get the periodicity right. So that's extremely promising when you look at a passive structure. The next order of business is to look at the modulator. The modulator itself is based on changing the guiding properties within that composite structure to alter the loss, not the absorption in this case, the propagation in this case. And that means you can have a relatively high extinction ratio with a relatively low voltage. Why is that important? Because that can allow you to have extremely small devices with very low energy per bit, hence low power consumption, that are, as you can see in the structure, non-resonant. Non-resonant means there is no resonance, means there is no or very low temperature sensitivity. Also, because these are plasmonic devices, they be very small. Their intrinsic bandwidth, which is dictated by either the transient time or the RC time constant, could be in the hundreds of gigs, as opposed to 56 gigs as we usually get from the best silicon devices out there right now. If you look at these modulators, you will find that the devices themselves are exceedingly small. They are like 2 micron square, the device area. That's orders of magnitude smaller than silicon. Yet, the losses in this device are only 1 dB. Again, better than silicon. That's extremely unusual. Silicon is the top, most efficient optical material right now, photonic material. How can one make a metallic structure that beats it at its game? If you look at the extinction ratio of the modulation, top-bottom plot, you will find that the extinction ratio is relatively stable across temperature. So this device is not thermally sensitive, which is a holy grail when it comes to comparing it with ring resonator devices, which offer the same but even worse temperature sensitivity. We've tested these devices for bandwidth, given what we have in the lab, and the equipment we have in the lab can go up to only 26 gigs, but as you can see, it's relatively flat there, and it has much higher bandwidth. What are the other components? The detector. We built a detector. These materials are based on amorphous active, not crystalline. And that's another huge advantage that can allow you to do passive and active photonics using amorphous materials. That's just, in comparison to silicon, relatively unheard of for detection particularly. Yet, using internal photo emission and junctions as the ones shown below, two metals surrounded by a dielectric, in this case an amorphous doped amorphous silicon, one can achieve Schottky junctions and can achieve photo emission. And here's a device that is 5 micron in length. 5 micron is approximately maybe 10 wavelengths in length. And if you look at its bandwidth, again, we've tested up to 26 gigs, which is the capability that we have. But look at the sensitivity. The sensitivity is a few orders, actually 3 orders of magnitude higher than crystalline materials. So this is the first time that one is able to get a better performance from an amorphous material compared to a crystalline one through just the addition of plasmonics in it. That's very unusual. The reason why this sensitivity is a world record is because of the dimensions of the device and the dark current associated with it. However, there is still room to making the responsivity, which plays a role in the sensitivity in the numerator, higher as well, which we're working on. Now that we made the devices and we saw what they can do and how they can perform, let's compare them to silicon photonics. So we have a model system, a sort of a typical system that we use to compare both plasmonics as well as silicon photonics and see how they fare. Putting the devices in the exact same system, you'll find that there is approximately a factor of 25 to 30 improvement for the same bit error rate in the data rate between silicon photonics and our plasmonic devices when we use the correct electronics. Meaning we don't use electronics that are used for silicon photonics. Why is that a problem? Because our devices are significantly higher bandwidth. So if you use the ones that are made for 56 gigs or 25 gigs, you obviously don't have a very large advantage. But most notably, because our devices don't have any latency associated with thermal stability, the latency of our devices is merely the latency of the electronics and the length of the distance that the light propagates. So a few nanoseconds. But because of photonics requires a significantly, silicon photonics, higher time to settle, it could be up to 600 nanoseconds, which is a killer for high performance computing applications, which aspire to go in the single nanoseconds. There's been a lot of work that has been done, particularly on the IR lab side, where they actually have taken this down by at least a factor of 2 or 3, but it's still in the hundreds of nanoseconds realm. So as you can see, there's a distinct advantage to what plasmonics can offer. If you look at other things like the channel bandwidth itself, there's a factor of 24 or more, or 20 or 30 higher. The bandwidth density is even more compelling because there is a factor of 70 enhancement, 70 enhancement. Within the latency standpoint, there's also a factor of 70 enhancement, and even on the energy per bit, which relates to the power consumption, even that plasmonics has an edge. Let's go back and assess that process where we have looked at a very effective efficiency metric, which relates to the figures of merit of energy per bit divided, the bandwidth density divided by energy per bit. And let's see how silicon photonics fares. Silicon photonics does very well at the longer distances at about a meter, which is depicted with the green plot here. So it goes within the area that we were trying to fulfill, but it's difficult to go to the left. If you use existing plasmonics before our work that use conventional plasmonics, you'll find that it's pushing the envelope a little bit. It's pushing that line and going into the quadrant we're trying to fill, but not by much because it's dictated by the losses associated with conventional plasmonics. If you look at our work, you will find that it is filling almost all of the quadrant because it goes up by about 1.5 to 2 orders of magnitude improvement upon what exists right now in conventional silicon photonics. But not only that, but it could also be built using non-crystalline materials. If we restrict ourselves to crystalline materials and compare to silicon photonics, we can do even much better. But if we say, no, I'd like the flexibility to build these on CMOS and take the real estate hit, or on the back end of line of CMOS and have zero footprint at all and keep the CMOS itself to electronics, it can do both. Silicon does not do both because it requires crystalline silicon. So that is almost an inflection point in this field. Why? Because now you can see that you can envisage a CMOS chip shown here with the blue electronics at the bottom of that chip, connected with lots of metal layers, the golden ones. But at the back end of line of every one of these CMOS chips, one can build a fully functional active/passive circuit with great or much enhanced density than what exists right now, but at the back end of line using no crystalline materials. So this can offer almost a new paradigm for how one can build electronics and photonics at the same time. This platform could do more than just data comms. It can do much better than just communications. It is really, I will only choose two in the interest of time, but there are many other examples of where that platform can contribute as well. I'll choose two ones. I'll choose optical communication example, and I will choose quantum computing or quantum transduction example. For optical communications, the size and the energy is important, but the size itself is not as critical. What is really important for optical existing and emerging versions of optical communications is the ability to have coherent detectors, systems. So the modulation format itself changes from being the amplitude modulation that we know and love, shown in the green spots on the top left. It involves phase, as an example shown on the middle top plot. Ultimately, when you can control these two simultaneously, you can have different modulation formats such as DPSK, QAM, etc., etc. These are extremely important in emerging and existing optical communication systems right now. It turns out that our platform can do that to some extent. It only requires significantly lower footprint. So if you look at a triode device like this, which is made out of the exact same few micron device that we showed you before, if you control the top and the bottom junctions, given where the field is, and you look at the propagation loss for that device, as well as the refractive index and hence the phase of the same device, you will find the following: that for a combination of voltages across both the two terminals on the device that I showed you before, there are two voltages, right? VB minus VA and VB minus VC. If you control these voltages, you can obtain plots like the loss and phase shown on the left and the right respectively. So you can obtain devices with losses being modulated between 0 and 1 while maintaining the phase constant, which is an ideal amplitude modulation with no chirp in that case. Or the opposite, you can have a device that swings a pi phase for the exact same amplitude. That is also an ideal phase modulator. Combine both together, and with the right voltages as shown on the top right-hand side, you are able to get a QAM modulator. And if you have a lookup table to get more voltages chosen, you can have much higher QAM or DPSK. That is an extremely important ability in optical comms, to be able to have very small, a few micron modulators. If some of you are familiar with the field of optical comms, you will realize that to achieve this function, you need a nested list of Mach-Zehnder modulators. Each is on the order of 0.5 millimeter. In our case, this is a 10 micron device. The huge difference in size. The figure of merit of these devices is particularly large because the energy is low and the extinction ratio is comparable to all the other devices. So our designs and platform offer almost a factor of 10 improvement on the figure of merit for modulators. On the detector side, for optical comms, because these devices are particularly small and they have very low noise, you will find that the sensitivity of these devices, albeit being amorphous, albeit being very small, are best in class and best out there, full stop. So they compete even with their counterparts that are plasmonic, and they also compete with silicon detectors that are crystalline or germanium detectors and still outperform. That is an exceptional advantage. If you go and look at other advantages that this nanoscale confinement can offer, quantum comes into mind. Let's take a look at this example. I will be extremely cursory and simplistic, just to make sure that we are all on the same page. Let's assume, for the sake of the argument, that you know nothing at all about quantum computing and quantum at all. Quantum computing itself, in a nutshell, can help really accelerate the expansion and the capabilities of compute, such as machine learning, molecular simulations, encryption and decryption, as well as recognition, including image. However, the size of any given quantum computer is very much dictated by the technology within which it's implemented. All technologies, some are more powerful than others, but it's fair to say that by and large, as the power of a given quantum computer goes up, the ability to scale that quantum computer to a larger number of qubits goes down. So you're left with this dichotomy of the power of the computer, its size, versus its number of bits or computing capability. So it turns out that one can increase the capacity of a quantum computer by connecting two of the same, quantum mechanically. So you just make two small ones, or four small ones in that case, and you connect them quantum mechanically. So let's assume, for the sake of the argument, that we have two quantum computers. Each one of them has only got 4 bits, like this example. This is a slightly dated example, but just to give you a feel for simple numbers. With each one has got 4 quantum bits, because two, when linked quantum mechanically, would behave like one quantum computer, the power, the computing power on the quantum scale goes up 16-fold, because it's 4 to the 2. So that is extremely exciting, especially when the numbers start to go up beyond 2 and 4. But how can one connect two quantum computers? I do apologize for those of us who are expert on this topic, but I'm just trying to get all of us to sing from the same song sheet, basically. So to connect two quantum computers, let's assume, for the sake of the argument, that here are 4 quantum computers in this case in the example A. What you would want to do is to get the quantum state of one computer shared with the other ones. In this case, how would you share them? The easiest way, it turns out, is to use photons, because photons maintain the quantum state over modest distances of propagation, definitely distances within a single packaged system where these 4 quantum computers can exist. So it turns out that photons can play a very important role for us to be able to connect quantum computers. In fact, more recently, photons have been used to connect some superconducting qubits using photons that are coupled with phonons. Why would we need phonons? Because if you look at this figure, quite simply, I will look at this from a higher level. You need to be able to connect a given qubit in the quantum computer. In this case, it's a superconducting qubit with another qubit. You need to find an intermediary. This intermediary would be a photon, usually around 1550 nanometers, so it can travel from A to B. But for this photon to be able to carry the quantum information, it needs an intermediary. And it turns out the intermediary for the superconducting qubits could be in the microwave range. And that's when phonons comes in. And the phonons could be the intermediary to connect the 1550 photon, given its energy, to the superconducting qubits. So the ingredients for us to be able to make these interconnections is to have entangled sources, non-classical sources, at the wavelengths, one at 1550 to move from A to B, and the other wavelength is dictated by the technology you have. If you have superconducting qubits, it's in the microwave regime in the gigahertz. If you have a CMOS qubit, it's in the terahertz regime. If you have a nitrogen vacancy or a defect, it's in the visible regime in red. As long as you cater that color to every single qubit, it's interfacing with. So where do we come in? If you look at the approach that I mentioned to you and the waveguides that we detect or we have identified and worked with, you will find they provide extremely high per cell factor, and hence they can be situated in extreme proximity with a very high Q with a given qubit. However, these devices are relatively low loss if they're only a few microns and have sufficient nonlinearities to be able to generate also entangled photon pairs. So then it's very easy that one can envisage that these devices could not only generate pairs, but also link them and couple them to several quantum computing fabrics. So what I've done is that I've spoken to you about two systems, silicon photonics and these coupled hybrid plasmonics that we've been developing over the last decade or so. And I've shown you how we were able to outperform silicon photonics in the field of data comms. And I've shown you also the potential of these plasmonic structures and how they can contribute to other fields such as optical comms, as well as quantum computing. And there are many others as well, including terahertz and optical phased arrays for LiDAR, but I just did not have the bandwidth to talk to you about them in this talk. If you're interested, drop me a line and feel free to inquire or otherwise. Here are a few references for your pursuit. Thank you so much.
Thank you so much. Any question? Well, greatly appreciate that the plasmonic circuits comparison to photonic circuits, because I guess that's the only plasmonic topic in this IZPHOTECH 2022 that give us a different fit and a different perspective. Thank you so much for that.
My pleasure. Thank you, Hasan. Thank you for the invite.
Well, we wish you a great day.
Thank you.
And I hope to keep in touch. Thank you so much.
Indeed. Thank you, Hasan. Thank you, everybody. Bye-bye.